So good morning, everyone. My name is Francesco Pavone, and it's an honor for us, for the Museum of Science, to host you here. For us, it's a mission, I would say, because this kind of congresses is exactly the ones that match so much with our mission, which is multidisciplinary. You are allowed to visit the museum. You can visit for free for these 3 days, and please, I encourage you to visit for a simple reason. I mean, this kind of Congress is putting together a lot of aspects. I mean, turning around the causality, which is a great concept behind coherence, beyond correlations, that allows you to go deeper in many, many fields, from economics to data science to genetics and so on and so forth. And I know that you're going to talk about that today and in these days. I want to add something, the beauty. Let me add the beauty. The beauty is what you will find here. And what you will find here is a perfect match between the knowledge, causality, and beauty. And it's fantastic to see all these experiments which are matching this concept of the progression of knowledge, which is causality, to my experience. In fact, in science, everything apart some fewer cases increase because of incremental aspects. But the beauty here, it's something that is merging everything together. Darwin was saying that together with the laws of evolution, the first two laws, which is the preservation of the species and the sexual attraction, the beauty was the third law of evolution. And I think that in the causality as well, the beauty plays an enormous role. So thanks for being here, and I would like also to say that it's a pleasure to introduce also here Marco Pierini from the University of Florence. Is the Vice Chancellor for the Technology Transfer, and Carla Rampichini, Director of the Dipartimento di Statistica at the University of Florence. I'm sorry, but the Director, Roberto Ferrari, has some personal family problems, so he cannot be here, but I bring his salutation on behalf of him as well, and I wish you a fantastic period here. So welcome.
Good morning, everyone. Ladies and gentlemen, it's really a great pleasure and an honor to represent the University of Florence and to welcome on behalf of the University of Florence and our rector, Alessandra Petrucci, to the Galileo Museum for this very important event. First of all, I would like to congratulate with the organizers, because you have put together really a panel of high level of speakers. Therefore, I'm sure these 2 days will represent a great opportunity for you to exchange knowledge and to develop probably new ideas, and perhaps to develop also new research questions. As already mentioned by Professor Pavone, this is a very multi and cross topic among different disciplines, and therefore one of my point is that I would like to encourage cooperation among scientists in different fields. We know that it's not easy, I wouldn't say to force, but to suggest, to encourage researchers to, discuss with experts in other fields, but we know that it represents really a great opportunity when we do it. So that's my suggestion. And last but not least, this event is organized by many different organizations, by many different research organizations. I think it can be the basis for further developing the cooperation in terms of research cooperation, but also in terms of student exchange and other type of activities. So I also wish and hope that really we can cooperate among us for even in the future. So I wouldn't like to waste your time, so I stop here my short welcome, and I wish you a pleasant stay in Florence and a pleasant symposium during the next 2 days. Thank you.
Now it works? Yes, thank you. So with a great pleasure that I welcome you here at this symposium. I'm the, oh, it works? Okay, I'm the chair of the Department of Statistics, and I would say that the symposium is organized by our department in collaboration with the Harvard Data University Initiative, the European University Institute, the Galileo Museums, and the Florence Center for Data Science. So the Symposium of Causality is also part of the events of the centenary of the University of Florence. And is one of the activities we planned in our Excellence project, a project financed by the Ministry of Research in Italy every 5 years to found the, let's say, the best department of state university in Italy. And our project focuses on causal methods and statistical learning. So this activity, these 2 days for us is a great occasion to share with you ideas and find inspiration for our project and research. So we are very happy to have you here, and I believe that your contribution can highlight our research in these next 5 years. And I would say also that with the help of our department here researchers, we organized some laboratories on statistics and probability that will be open on Saturday for Bright Night, another event that will take place in these days in Florence, organized by the University of Florence. And if you are curious, you can see these laboratories during the coffee breaks. They are here in the same place where we are for the conference. So I want to thank everyone who organized the symposium with us and those who are participating. And I hope you will enjoy the event. And I give the floor to my colleague, Fabrizia Meali, who is the scientific coordinator of everything, and she will introduce to you to the symposium's keynote. So, welcome.
So before introducing our first speaker for the day, I would like to thank you all for being here. As I said also yesterday, to those who joined us for the welcome reception, I'm really happy and honored to have you all, and also thankful for having accepted to participate and contribute to the symposium. I'm here not just as one of the organizers, but also representing the Society for Causal Inference, for which I'm currently serving as president. The society is still young, but I hope that it will soon become home for communities, events like this one around causal inference in the world. And also I'm a kind of, it's a little bit emotional for me to see some of my students and even TAs from Harvard and also the University of Florence here. So it means not only that I've aged but also that I possibly have taught you guys something useful in causal inference. Not even among the audience, but also some of the keynotes and panelists were my former students. So I'm very proud of you and myself. So the symposium is organized around 4 keynote talks and 4 roundtables, which are meant to show how pervasive causality and causal inference is in many areas of science. And again, each of the keynotes is going to be, keynotes and roundtables are going to be followed by Q&A sessions with discussions from all of you. So please ask questions and be engaged. The event is actually streamed, or is being streamed at the moment. And it's going to be recorded for the posteri. So I guess without further ado, I'm going to now introduce our first speaker. I don't know, Guido, if you want to come up here. So our first speaker is Guido Imbens. I don't think that by now Guido needs a lot of introduction. So Guido is known for his work on causal inference, for which he received the 2021 Nobel Prize in Economic Sciences that he shared with Josh Engrist and David Card. I've known Guido now for over 20 years, and this is, I think, the 4th time I'm presenting him before a talk or a lecture. And the first one was pre-COVID, pre-Nobel, and the other 2 were post-Nobel. And I must say, the things that I can say about Guido haven't changed much, despite the Nobel. So Guido is renowned among his students and colleagues, not only for his sharpness, but also for his generosity in terms of collaborative work and mentoring. And so this was also, we could see that over the last week. I think this is the 6th talk he's giving, starting last Saturday in Rome and finishing with the 5th talk yesterday to the students for the centenary of the University of Florence. So let's welcome Guido, and Guido, the floor is yours.
Thanks very much, Fabrizio, for the introduction. Thanks, organizers, for organizing this. I think the first time I was in Florence was when I was just finishing graduate school in 1990. And I've been back that was a very pleasant visit. It was a conference at the European University Institute. This was incredibly nice. And I've been back many times since then. It's always been an incredibly pleasant experience. So what I want to do today is kind of talk about some of the work I've been involved in on causal inference with panel data. There's been a lot of work in the econometrics literature, kind of in general, in the social science literature, as well as in other fields on these settings. And there's been a lot of interesting new methods, in particular synthetic control methods developed by Alberto Abadi and colleagues in various forms that are very widely used, kind of not just in academics, but also in the private sector and in lots of different disciplines, with lots of contributions coming from various disciplines. And so what I want to talk about is some of the things where I feel that the literature isn't very satisfactory. I kind of suggest some ways we may be able to improve things. Where are the arrows? There we go. So I want to look at a relatively simple setting, and so some of that means that sort of applying these methods is actually going to involve some additional work, but I want to focus on some of the conceptual issues. So I'm going to look at a setting where we have a panel, we have a complete panel with n units and t periods, and for the type of applications I'm interested in, both n and t may be modest, but kind of on the order of 20, 30, or 50. And so each unit period pair is characterized by a pair of potential outcomes, y0, y1, and a binary treatment denoted by W. And what we actually see is the matrix of treatments and the matrix of realized outcomes. So either y0 if a unit period is in the control group, or IT1 if the unit period is in the treatment group. And for simplicity, I'm going to focus on the case where there's just a single unit period that is actually treated. The methods I'm going to talk about apply much more generally to general patterns in the assignment matrix, but some of the methods that have been proposed in the literature rely on there being relatively few units treated or relatively few periods treated, and so it makes it easier to put all of them in the same perspective and compare them directly by focusing on the case, but it's just a single treated unit period pair. And again, kind of to focus on the conceptual issues, I'm going to abstract from the presence of additional covariates, of additional exogenous covariates. In practice, of course, they're going to be present and they often need to be taken into account, but they don't raise a lot of conceptual issues, and what I'm going to say is not really going to contribute to insights about how to treat these exogenous covariates. And what we're going to be interested in is what the causal effect is of this intervention on the particular unit period that was actually treated. And so in addition to abstracting from the presence of covariates, I'm also going to abstract from dynamic effects. Most of the time, actually, I'm going to look at a case where it's only in the last period that a particular unit was treated, so we don't really have to worry about dynamic effects. The presence of dynamic effects is very important. I'm going to make some comments on issues related to that, but again, it introduces more difficulties, and I want to focus on issues that arise even if there's no dynamic effects present. And so kind of what we see what the data are going to be like is this n by t matrix of outcomes, and then this matrix of binary assignments that is all zeros other than a single entry that is equal to 1, and we're going to try figure out what the causal effect is in that particular period for that particular unit. In order to do that, we see all the y0, we see the y1 for that particular unit period, we don't see y0, we have all these other control outcomes, and we're going to use those to impute that one particular missing control outcome. We're going to look at different ways of doing that. As I said, there's going to be more general assignment mechanisms that are important in practice. It could be completely general, that there's treated unit period pairs all over this the periods and for different units, and there's often kind of more structure on that. The staggered adoption case, where you see units adopting a particular treatment and then remaining exposed to it forever after, is a very common setting in practice. And so the some of the methods I'm going to talk about apply to that case, but others actually have a lot of difficulty dealing with some of these more general patterns. And that's why it's useful to focus on that case where it's just a single treated unit period. And so for that setting, there's lots of existing estimators. And the most popular one in much of the social science literature is known as difference in differences, or two-way fixed effect methods. And so you can, one way of characterizing that in this setting is just as a least squares regression estimator, where you regress the outcome that is observed for all the units, all the unit period pairs, for the n units in the t periods. We can characterize it as a regression estimator where we regress the outcome on unit fixed effects, so on indicators for the units, indicators for the time periods, and an indicator for the treatment, and the coefficient on the treatment that is interpreted as the estimated effect of the treatment. That's a hugely popular way of estimating the treatment effect in this case, and in other cases. This is one of the estimators that applies to general assignment mechanisms in this case, including staggered adoption, but any assignment mechanism where the treated unit period pairs are spread out all over that matrix. There's a lot of variations on these estimators. Some of the recent work has raised concerns for the staggered adoption case that implicitly we put negative weights on some of the treated outcomes for some of the units. There's other variations in the political science literature, some of the work by Kosuke Imai, but kind of for the basic setting I'm looking at here, where there's no covariates and just these outcomes, this is kind of the simplest version of that. Now, in the early 2000s, kind of in the application, I think in 2001, but with the key paper, the JASA paper in 2010, Alberto Abadi introduced a different class of estimators, he labeled synthetic control estimators, where instead of estimating the effect by just averaging outcomes for changes in outcomes for all the control units, he focused on creating a set of weights such that the weighted set of control outcomes matched the outcomes for the treated unit in the pre-treatment periods, in control periods. So kind of specifically you can interpret that estimator also as being based on the least squares criterion, where if the treated unit is treated in period capital T, you regress the pre-treatment outcomes for that treated unit, unit n in this case, on all the outcomes in the same period for the control units, get the weights from that regression, where in the original formulation these weights were restricted to be non-negative and summing to 1. That gives you this synthetic version of the treated unit, and you use that, you apply those weights in the post-treatment period to impute the missing potential outcome, and then subtract that from the actual outcome to get an estimate of what the effect of the treatment is. This kind of variation, there's again, as in the difference in difference setting, there's a lot of variations on that. Once you have that regression interpretation of the estimator, you can imagine also allowing for an intercept in that regression. And the nice feature about that is that it then it directly generalizes difference in differences by having just the weights be different from 1 over the number of controls, but allowing that to make sure that you get a better match to the treated units. There's other estimators. I'm going to focus here on one particular one, sometimes referred to as interactive fixed effects, kind of with some of the work going back to Yiching Xu, where in addition to having the unit fixed effects, the unit fixed effects and the time fixed effects, there's also a low rank component in the regression function here denoted by LIT. So in principle, you can now fit the objective function exactly by just setting the LITs equal to the outcomes, but by regularizing that, and a popular way of doing that is using nuclear norm regularization. You force the matrix LIT to be a low rank one, and again you can think of this as generalizing difference in differences by allowing more complex correlations between the units as well as over time. In principle, you can actually subsume the unit and time fixed effects into this matrix, but in practice, it's very helpful to include those without regularizing them. One final set of estimators in work I did with Susan and Stefan Wager and Dmitry Arkhangelsky, we're also here. It's the synthetic difference in difference estimator. It actually combines kind of features of both difference in differences and synthetic control, where we use the difference in differences criterion, kind of the square difference between the outcome and the unit and time fixed effects, as well as the treatment indicator. But then, like the synthetic control estimators, we use a weighted version of that criterion, where we use the synthetic control weights omega I, as well as the time weights lambda t, to make it more symmetric and to kind of take account of the fact that typically you would think that some periods are actually more helpful, more useful for imputing the missing outcomes than others. So, what is my concern with this literature, kind of with these particular estimators? And again, I'm not trying to criticize the literature here as much as kind of raise some general issues, and some of these estimators have been involved in. But the concern kind of with the 4 estimators that I described at the moment is that they don't really take account in a very principled way of the time series dimension of these data. They essentially take this matrix of outcomes as both row and column exchangeable. For the units, that may be a reasonable thing to do, but it's clear that we don't really think of the time series component as exchangeable. And so how does that show up? If you were to take these data and reorder the columns of the matrix, or threw away the labels of the time series dimension, it wouldn't really change how you would estimate the treatment effects. And of course, that doesn't really make a lot of sense. If you were given the data and someone said, well, do you actually want to know which periods these data correspond to? Do you want to know whether this is data from 1988? You know, we're trying to impute the values, say, for 1990. Do you want to know whether these other data are from 1989 or from 1970? It clearly would be very valuable to know the time labels. And we think that in fact, the data in more recent years should be much more informative about the effect of the intervention, should be much more helpful in imputing the missing data than the data from earlier periods. Because implicitly, that is being used a little bit, if you think about one of the canonical applications in this literature using synthetic control methods, where Alberto Abadi and Heinmüller and Diamond are trying to estimate the effect of German reunification. They use data on West German GDP from, I think, 1960 to 1989. They don't go back to, say, 1910, because clearly things were very different there. They do think the recent years are more informative, but they do that in a very ad hoc way, by just using data up to from a particular point in time onwards, rather than actually allowing for the most recent years to have more influence on the estimates than the more distant years. So this idea that we should be using these data as if they're both row and column exchangeable doesn't really seem very plausible. But yet all these estimators, and again, these difference in difference estimators, incredibly widely used, and the synthetic control methods are very widely used. But it also includes these matrix completion and synthetic difference in difference estimators. These are all treating these data as if, in fact, they are row and column exchangeable. And I think it's clear that we should be able to do better by really taking account of the time series nature, of the time series property of these data. The second part, and I'm going to come back to that, I'm going to continue on the estimation for a bit, and then I'll come back to the inference part. Second is that it's not clear how to do inference in these settings, and that there have been a number of methods that have been proposed, essentially kind of coming from the difference in differences literature, regression-based estimates, where people really lean into the regression interpretation of these estimators and use standard robust methods for getting standard errors, as well as placebo methods, where in one of the Abedi Diamond Heimer papers, they suggest pretending other control units were in fact treated, estimating the effects for those control units, and then using that to get a sense of the variation in there. And there's some conformal inference methods that have been proposed there. What I'm going to do is kind of put those on a slightly different footing and show how they relate to each other and why choosing between them is going to raise issues that haven't really come up in part of that literature. And I'll talk a little bit about kind of what the appropriate, what I think is a useful way of thinking about the repeated sampling thought experiment. But kind of first, let me say something on estimation. And so here, I want to just introduce one new estimator, not because I think this particular estimator is necessarily so much better than other possibilities, but just to kind of to show you that it does actually make a substantial difference, taking account, even in a relatively crude way, of the time series nature of these data. And so what we do here is essentially use the same criterion as in the matrix completion paper. We have a square difference between the outcomes and a regression component that has a unit fixed effect, a time fixed effect, and this low rank component, the LIT, where we're going to use nuclear norm regularization on that low rank component. But then we're going to weight those square differences. We're going to weight those in two directions. We're going to weight them in terms of the units, not using the synthetic control type weights, but just directly using matching type weights, where we match, we try to give more weights to units that have the same control outcomes in the periods that they were in the control group. And the big advantage of using this type of weights relative to the synthetic control weights is that it allows us to deal much more easily with complicated assignment mechanisms. The synthetic control weights are essentially regression weights where you need to do a regression, and there the missing data that would come from the general assignment mechanisms makes things much more complicated. Here we just only use the periods that units are in the control group, and that allows us to calculate these weights kind of very directly, irrespective of what these assignment patterns are. Then the second component of the weights is these time weights, where all we do is weight things, give things higher weight if they're close to the period where we're trying to impute things. And we have a tuning parameter there, lambda t, that measures how quickly these weights decay over time. So instead of giving all the units, all the time periods equal weight, if we're trying to impute the outcome in the year 2000, we'll give more weight to 1999 than to 1980, and we have these weights decline in a smooth way. And so then we go to estimate these, choose these tuning parameters based on cross-validation, and see what how well we do with those weights. Okay, and again, I don't want to push this as this is kind of the right way to think about these weights, but what I do want to stress is that it's just going to be important to take account of the time series dimension. That's going to make a substantial difference in the performance of these estimators. But there's additional things you could do. If you have covariates, you could bring those in and have an additional set of weights corresponding to those, a little bit in the spirit of Imai's work. You could weight things in terms of the assignment pattern. But the next thing I want to do is actually kind of show a little bit how that works in practice. Of course, it would be very easy to come up with simulation designs that make that estimator look good. But what we try to do here is show some results for somewhat realistic assignment mechanisms. And so we actually took the simulation designs we had used in an earlier paper, the synthetic difference in differences paper, where in that paper itself, kind of we tried to be very realistic in the simulation designs. And so we took a bunch of actual data sets, estimated a very flexible model on that that had a rank 4 component, as well as fixed effects. We estimated an autoregressive process for the residuals, and then we estimated an assignment process that was related to real regulations, kind of when we were using state year data, so that we had an assignment mechanism that was in fact correlated with the outcomes, but uncorrelated with the residuals. And so we did it for a bunch of different data sets, some based on the current on the CPS data, as well as so where we have state year data, as well as some based on the Penn World tables where it's country data, and we focused on GDP as the outcome. And so in the SDID paper, we compared a bunch of different estimators, including difference in differences, matrix completion, synthetic control, as well as the synthetic difference in differences. And you see here, and this is mainly driven by the time series smoothing, by the additional tuning parameter coming from the time weights. You see that in all cases but one, this new estimator, by having these weights over time, outperforms all the other existing estimators, and in the one case where it doesn't, it's actually a very close second. And again, kind of from the 3 sets of tuning parameters, it's in particular the time weights that matter. In practice, even if we have 40, 50 years of data, if we're trying to impute things in the last period, it's really the last 3, 4 periods that get much weight. And the tuning parameter for the time weights is substantially different from 0, and it really downweights the data from even just a couple of years away from the treated period. So again, I don't want to push this as this particular estimator being so useful, but that we need to take much more systematically account of the time series dimension than much of the empirical literature is doing by using these the difference in differences to a fixed effect methods, or even the synthetic control methods. The idea that the data for many years before is actually very useful doesn't seem to be very realistic, given that many of the variables that are used in the empirical applications tend to trend in ways that make the earlier years much less informative. So let me then change and kind of talk a little bit about the inference and variance estimation. In fact, I'm not really going to talk that much about the inference part, because I'm going to focus on this case, but it's just a single treated unit period pair. So I'm just going to focus on trying to get an estimator for the variance. And so I'm going to look at a case where the control outcomes have two components. There's a systematic component, mu it, and a noise component. I'm going to assume that one of these methods, whichever of these methods we use, is reasonably effective in estimating the systematic component. And so if we want to get the variance, what we need to do is estimate the variance for the residual for the particular treated unit period pair. So continuing to focus on the case where it's unit n that is treated in period t, what we're trying to do is get the estimator for the variance in that particular period for that particular unit. So we're trying to estimate sigma and t squared. Now, what have people done in practice? Sort of one common approach, kind of going, sort of originating mainly in the difference in differences literature, is to focus on the regression interpretation of these estimators. And so in cases where you can write it as a regression estimator, you can just use the standard robust variance estimator and then focus on the component, not for the unit or time fixed effects, but just on the component for the coefficient on the treatment indicator. And essentially, that is what that corresponds to. Let's go to approximately take the estimated parameters, get all the residuals, epsilon and t, square them, and average them over the whole matrix. So it's just getting the residuals, average the squared residuals over the full, over all the n times t minus 1 control outcomes, and use that as an estimator for the variance for unit n in period t. Now, in the synthetic control literature, people took a very different approach, and it's what they did was essentially go through all the other units. So if there's only a single treated unit, go through all the other n-1 control units, pretend for each of them in sequence that was the treated unit, estimate the treatment effect for that particular unit, compare it to 0, because the unit was actually in the control group, so the treatment effect was 0. Compare that to the actual value, take the difference, that gives you the residual epsilon I capital T in this case, because all the treatment happened in period T. Average those squared residuals, now not on not over the full matrix, but just in the last period, in the treated period. And so average the residuals over all the control units in the last period, and use that as an estimator for the variance for unit n in period t. And kind of interpreting that placebo estimator that way as just estimating these residuals in whatever way you want to do that, and then averaging them just in the last column for the matrix. Obviously, you could do the same thing, but then in the time series dimension, and that has been proposed as well. So you could take the residuals for the treated unit in all the other time periods, square those and average those, and get another variance estimator based on time placebo methods, or the conformal methods as they're referred to in the Chernosikov et al. Paper. So kind of to put us on the same footing, and in fact the way they're typically implemented is slightly different, but you can think of them in all cases as you estimate the treatment effect for a particular unit, say unit n in period t, then to get the variance, you use the exact same methods to estimate the residuals for all other units, for all other time periods, and then the variance for unit n in period t is estimated by averaging the square of these residuals, where the choice is which set of residuals you're averaging over. difference. In difference approach, you would be averaging the squared residuals over all other n times t minus 1 control outcomes. In the unit placebo case, you would average just over the control units in the same period. And in the time placebo method, you would average over all other time periods for the same treated unit. And kind of what the literature has focused on in these papers is largely on conditions under which these different variance methods are consistent, are unbiased, at least in large samples for the variance. But I want to go here a little beyond the validity of these variance estimators and think a little bit about how to think about the choice between them. And so the first exercise I want to do is following. So I take one of these data sets here from the current population survey, so where we have data for 50 states, 40 years. And so for each of the 2,000 entries in that matrix, I'm going to calculate the estimated treatment effect, which of course is estimating 0 because there's nothing going on here. And I'm going to calculate for each of these 2,000 pairs IT, I'm going to calculate these 3 variances or the standard errors in this case, and I'm going to compare them. And so so here, this is actually done for 2 data sets, so the CPS where I took log weights as the outcome, and for the California smoking data set, which is one of these data sets that's been used in the synthetic control literature. And I'm going to do these calculations and look at the comparisons between these 3 variances estimators, as well as the 4th one that I'll introduce in a little bit. And there's sort of a couple of interesting things that come out of this that hold more generally. First is that on average, the standard errors from these 4 methods actually very similar. And in fact, kind of on average, they correspond more or less to the standard deviation of the estimator over these 2,000 entries in that matrix. And actually, I should have included that column here as well. That's going to lead to the coverage rates for confidence intervals based on these standard errors to be more or less right. So these confidence intervals aren't necessarily valid because there's no reason to expect these residuals to have normal distributions, and there's only one treated unit period pair. But the coverage rate is actually not bad for any of these variance estimators. And so they're fine on average. But in the second column, you see that there's a substantial difference between the standard error estimates in terms of their variance, in terms of their standard deviation. You see that the marginal variance, the one based on averaging the squared residuals over the entire matrix, doesn't vary at all, kind of depending on which unit period pair you're trying to impute. It's pretty much the same every time. The standard deviation here is, in the top part of the table is 0.01. If you do the unit placebo standard error, or you do the time placebo standard error, the standard deviation of that standard error is much, much bigger. It depends a lot on which unit you're doing this for, or which time period you're doing this for. And in fact, the correlation between these different standard errors tends to be negative, if anything. And so it's going to make a substantial difference which one you use in practice. And so, I did this for the 2 data sets here, kind of just to show you that that's not specific to one particular data sets. You see that in general, and in the second case, again, you see that on average, these standard errors are pretty much the same, but the variation of these standard errors differ substantially between these four methods, and a lot of the correlations tend to be negative. So I want to think a little bit now about how we should think about choosing between these estimators. So given that we see that they're more or less correct on average, but they have a lot of the variation differ substantially, and we have these negative correlations. So I'm going to simplify the example even further now and look at a case where where the systematic part of the potential outcome is actually zero. So the potential outcomes are kind of all noise. So in that case, the estimator is very easy. We would just impute the missing potential outcome as zero, and the error we make is just the residual, and we're going to try to estimate the variance of that residual. And now, suppose we're willing to assume that this matrix of residuals is row and column exchangeable. Now, I kind of started off in the estimation part that I didn't think the matrix of outcomes is going to be row and column exchangeable, and so in practice, I would be worried whether that was true for the residuals as well, and so we may need to do more in terms of actually taking account of the time series dimension and model some of the autocorrelation structure for these residuals. But I'm going to abstract away from that, and I'm going to assume that we've done that already, and that in the end we have these residuals that may have heteroscedasticity, but that are in fact row and column exchangeable. And that's going to be very helpful for interpreting what these different variance estimators are going to do and how to interpret them. So once we have the row and column exchangeability, we can think of these residuals as having a structure where they are some unknown function of a unit-specific component nu I, a time-specific component psi t, and an idiosyncratic component eta it, with all these components independent. And so I'm going to assume that these residuals have mean zero for all units and time periods, but that it may have a different variance. And so now we can kind of think of there being four variances we may be interested in. We can look at the marginal variance, the unconditional variance of the residuals epsilon it. We can look at the conditional variance for a particular unit, and given that all the conditional means are zero, that would be useful variance as well for doing inference. We can look at the conditional variance given the time period, so that's going to be a function just of psi t, where the unit-specific variance is going to be a function of kappa and nu I. Or we can look at the conditional variance given both the unit and time components, given both nu I and psi t. And so the expected value of all these variances is going to be all equal. All of them, in principle, are valid, given that we've assumed that the conditional means are all zero. So in principle, all these variances are going to be fine in terms of doing inference. All of them are going to be valid unconditionally. But of course, that doesn't mean that the choice between them is immaterial. There's going to be an ordering of these variances in terms of how variable they are. The marginal variance obviously has the smallest variance. The conditional variance has the biggest variance, and the unit and time variance are in between, and you can't generally order those two. How does that help us in terms of deciding which is the most useful variance to actually use? Well, here we can go back kind of to one of the old Cox papers about whether to do conditional inference or marginal inference. So if we have a setting where we do an experiment, where we first flip a coin whether to use one measuring instrument or another measuring instrument, and assuming that one of them is very precise and the other one is not. If we look at the measurement after the second stage, we can look at the variance of that measurement unconditionally or conditionally on the measuring instrument. Because there, Cox argues that we should, that even though both variances are valid, we should use the conditional variance. That is the one that is useful in practice. So what does that mean in the case we're interested in? It certainly means we shouldn't be using the marginal variance. We should be using one of the conditional variances. And ideally, we would like, just going back for a second here, ideally we would like to use the conditional variance, where we condition both on the fact that we know we're trying to impute things for, say, California in 1990, not just that we're imputing things for California, or not just that we're imputing things in 1990, but do both. And it's less clear whether we would prefer to use the conditional variance for California or the conditional variance for 1990, because we can't rank them, but we certainly shouldn't use the unconditional variance, because that's going to be less precise for the particular case. So, going back kind of to the case we're interested in, using the marginal variance, kind of we lean into both the row and column exchangeability. We're using all the squared residuals, and that is essentially estimating that unconditional variance, which is the one that is the least attractive, because it's not conditioning either on the unit treated or the time period treated. Using the time placebo variance is leaning into the time component and is conditioning on that. Sorry, and is leaning into the unit component, is conditioning on the particular unit. And using the unit placebo variance is conditioning on the particular time period that is treated. And so the conditionality principle suggests we would prefer either the time or the unit placebo to the unconditional one, but in fact we would really like to use the conditional one where we condition on both. Now, of course, that is not actually that is not actually possible. We don't have multiple outcomes for the same unit for the same time period, so we can't directly estimate what the variance is for California in 1990 in the smoking example, or for the effect, the conditional variance for Germany in 1991, because we only have a single observation there. We can estimate the unit placebo variance and condition just on the time period using all the other countries in that same year, or we can use the time placebo variance and estimate the conditional variance just for that particular country, but we can't do both at the same time, which is what we ideally would like to do. So what should we do in practice? So that there's going to be some compromises that have to be made. If we want to be sort of non-parametric there, we can condition on either the unit or the time period, but we can't condition on both. But in practice, we would expect that to be heteroscedasticity in both dimensions. And so we may do better in practice by making some assumptions about how that, so the form of the heteroscedasticity. So we do capture some of the time heteroscedasticity, as well as some of the unit heteroscedasticity. And so what I want to look at next kind of is think a little bit about building a model for the heteroscedasticity and see how well that does in terms of capturing the best of both the unit placebo and the time placebo part. And so what we're doing here is modeling. So build a model here, we need a model for the conditional variance. So in terms of the unit and the time component, we do that by specifying a two-way fixed effect model for the log of the conditional variance. So we're assuming that the log of the conditional variance has a unit component ui and a time component psi t, and they're both additive in the log of the variance. We then estimate these using all the squared residuals, and then we transform that back to an estimate of the conditional variance. Because we're estimating this model in logs, and then we're transforming it back, taking the exponents, we kind of need to take account of the fact that the expectation of the log is not the log of the expectation, so we end up adding a constant there, this 1.704, that comes from assuming normality, but that's kind of not all that important. The key thing is that what we're doing now is building a model for that conditional variance so that we can use all the residuals to help us estimate what the variance is for a particular unit, say California, in a particular time period, using the residuals for California in all the other years, using the residuals for all the other states in that same year, as well as kind of the residuals for all the other states in all the other years, and kind of we combine them all to get a better estimate of what that conditional variance is. To kind of get a sense of how much difference that's going to make, I'm also going to do some additional calculations so we normalize so we estimate these unit components for the variance. Actually, I switched the notation a little bit here. These were the new i's and psi t's from before. And I want to think of these, of each of these unit fixed effects as coming from a chi-square distribution, and look at the degrees of freedom to actually get a sense of whether there's more variation in the time series component of the heteroscedasticity or the unit dimension of the heteroscedasticity, just to get a sense of where the variation is. Okay, so here's a table where we're trying to implement that. So now, again, we look at a couple of different data sets, and we're going to focus mainly on the second row here for the current population survey, where ours is the outcome. So we have 50 states, 40 years. We estimate all these pseudo-treatment effects, and we see how well the different variance estimators, different standard errors do. Here, we do actually have the coverage rates in here as well. And so we're going to compare the unit placebo standard errors, the time placebo standard errors, the marginal standard errors, and these conditional standard errors, where these conditional standard errors are based on estimating this two-way fixed effect structure in the log of the variances, and then kind of turn that back into an estimator for the variance. And so what are the key things? So let's kind of start with the marginal variance, kind of the three columns there. The average standard error is 0.64, and that's pretty much the same as it is for the other variance estimators. The unit placebo also has 0.64 as the average standard error, time placebo has 0.63, and the conditional standard error is on average equal to 0.66. So the averages of the standard errors, again, are very much the same using these different methods. But even though they're the same on average, they have a very different standard deviation. For the marginal variance, the standard deviation is essentially 0. For the unit placebo, it's 0.09. For the time placebo, it's 0.14. And for the conditional one, it's 0.24. The conditional one varies much more because it varies both across units and across time periods. And the importance of having the additional variation is that in the end, it's going to give us much better power for actually detecting effects when they're there. By not averaging all the residuals, you're going to be able to have much more power in a particular case to actually detect whether there's some treatment effects. And I'll show some graphs, some power curves in a little bit. Last, the kind of third column for all these estimators has the coverage rates, and again you see that for the marginal and the time placebo it's exactly 0.95. For the unit placebo and the conditional one it's 0.94. On average, all four of these standard errors actually do fine, but how they do in a particular case is quite different. And what you see here is that it's the implicit degrees of freedom in the time series dimension is much higher, it's much larger than what it is in for the units, and that's why the time placebo standard error has a much bigger standard deviation than the unit placebo one. So there's much more heteroscedasticity in the unit dimension than there is in the time dimension, and that's why you would be better off using the time placebo variance than the unit placebo variance. But both again are much better than the marginal variance. And you kind of see similar things for some of the other data sets. What's interesting again is that whether the unit placebo or the time placebo variance does better, is going to do better in terms of power, varies a huge amount. In some cases, there's much more heteroscedasticity in the time dimension. In some cases, there's much more heteroscedasticity in the unit dimension. So it's not the case that in general we should be using unit placebo or time placebo variances. Their performance is going to be very case specific, and it depends on where the heteroscedasticity is. Now, kind of to illustrate this, now I'm going to do this in even more stylized setting, kind of just to see how whether the intuition is right here. So now we're doing this in a setting where we simulate the data, we have normal errors, and we're allowing the variance to have heteroscedasticity either in the time dimension or in the unit dimension or in both, kind of where these C's have chi-squared distributions, and we're going to compare four cases. One where lambda unit and lambda time are both equal to 0, so in fact we have homoscedasticity. One where we only have heteroscedasticity in the time dimension. One where we have heteroscedasticity only in the unit dimension, and one where we have heteroscedasticity in both directions. And so here's what the power curves look like with these simulated data. So if there's homoscedasticity, kind of all four of these variance estimators do fine. Because in fact, the marginal one is going to do slightly better because it's estimating it more precisely, but it doesn't actually play a big role. The unit placebo, the time placebo, and even the conditional one do perfectly fine. Then if we only have heteroscedasticity in the time dimension, then the unit variance estimator is going to do much better because it's estimating the variance just using data from that same time period, so it sort of uses the time heteroscedasticity, and it's focusing just on the data that have the same time component, and that's going to lead to much better power properties for the unit placebo one. If the heteroscedasticity is just across units, then the time placebo one is much more powerful, and the conditional one kind of capture that as well. And if we have heteroscedasticity in both dimensions, then can we get the most interesting case? Now the conditional one is capturing both and doing much better. The unit and time placebo ones do better than the marginal, but not as well as the conditional one. So in all these cases, all of the standard errors actually are valid and give you the right coverage on average. But if there are treatment effects, there's going to be substantial difference in how well they do in terms of power. And again, if you want to think of it as a choice between the time placebo and the unit placebo, that depends a lot on where the heteroscedasticity actually is. The conditional one, in principle, tries to capture both, but it does rely on some modeling. And we can't really get around that because we don't have replicates for the same unit period pair. We need to do some modeling to bring in the data from the other units or the other time periods or both. And so there's going to be some compromises. Now, we do the same thing for some of the real data sets, and there it's not quite as clear. For the hours case, it doesn't seem like there's a huge amount of heteroscedasticity, so none of the power curves differ very much. For the other cases, the reason things are now not as clear is now we need to worry about the biases as well. In the simulated data, we specified the model correctly, and so there was no concern with the mean part. Here, we did this using a very crude estimator, namely just the difference in overall means, and so that's making these plots look worse than if we actually had an estimator that took out most of the systematic part of the potential outcome. And so we're now working for on these applications to actually get better estimators and seeing what the power curves are looking like there, and that's looking a little better. But so in principle, I think, let me wrap things up a little bit. Variance estimation intrinsically is going to be very tricky here, especially in these settings that are now very common in empirical work, where there's very few treated units and very few treated periods. The focus has largely been in the literature on establishing conditions that make the various variance estimators valid. And of course, that's the first order issue, but it's not the only issue. And partly there have been a bunch of these different estimators that may in fact be valid in many cases, but are going to be very different in terms of their properties in practice. And power is going to be one important reason for thinking about when thinking about the choice between these the existing estimators, as well as for developing estimators that have even better properties than the existing ones. So, summarizing the whole talk, I think that even though there's been a huge amount of work in this literature in recent years, in particular the work on synthetic control has happened in many disciplines, including many of the social sciences, statistics, and computer science. But there's still much more to be done, and I think many of these estimators, and there's some exceptions, but I think many of these estimators are not taking the time series dimension nearly as seriously as they should, and as seriously as some of the earlier literature in the 90s on panel data was doing. I think the recent literature has focused on very interesting issues compared to that earlier literature, but it's forgotten some of the lessons from that earlier literature, that the time series component is actually quite important. And so in practice, I think we also need to take some of the lessons from the cross-section evaluation literature, that it's important to model not just the conditional outcomes, the way, say, the difference in differences literature uses the two-way fixed effect models, but to also model the assignment mechanism and to combine those in more robust, in double robust type approaches, and that may be through weighting, and maybe through estimating influence functions, but finding ways that actually combine the assignment mechanism with better models for the outcomes. And in particular, I think with the differences literature, the idea that when we have on the order of 50 to 60 units and 40, 50 time periods, the idea that we can capture the full range of dependencies just through these time and unit fixed effects is just very hard to believe. Kind of when we're trying to predict what's happening in California, the idea that Delaware is completely comparable after we just take out the level differences doesn't seem very realistic. And you see that in a lot of these simulation studies that have been based on more realistic settings, that in fact, for any particular unit, whether it's a country or state, using units that are somewhat comparable is going to help you do much better than building these global models, these very parsimonious global models. And then on the variance estimation, it's clear that there's a lot more work to be done, where again we take serious the fact that there may be heteroscedasticity both in the unit and time dimension. And exactly how to do that, it's going to be tricky because it's going to involve some modeling, and so it's not going to be completely assumption free, but we should at least get a range of methods there that can allow for some of that. So let me stop here and open up for questions.
So, how do I switch it on? Can you hear me? Is that okay? I don't know how. Is it on? Okay, good. So before opening the Q&A, I just wanted to make a general comment that the symposium is not just about interdisciplinarity, but also to, see where we stand in terms of methods, and also what are the open questions and the challenges ahead of us. And I think this was a nice account of where we stand in terms of these panel data methods. So thank you, Guido, for your nice presentation. And so who wants to break the ice and ask questions? Everybody. So I don't know. First, Francesco.
Well, thank you for a lovely lecture. Two kind of question comment. So one is, I'm wondering if you have thought, or maybe there is in the literature, the same idea of accounting for the time series structure of the data, you could also account the replacing T by S. And what I mean by that is thinking about the spatial structure. And so it seems to me that it's almost exactly the same framework replacing T with S. And often I know you're thinking of the unit, you're thinking about sometimes the space, but you can take, spatial data, right? And then similarly, then the immediate next step is also thinking about space and time. And so I could see how, this can be, and I know that, in the econometrics literature, you're always thinking about the panel data, but this will be also, I think, in the context of spatial data and spatial temporal data. So just a comment. And this is a question from a Bayesian perspective. It seems to me, and again, maybe I'm missing something, but as a Bayesian, it would be so much more straightforward to think about all of these variance components, especially at the unit level or at the time level by building Bayesian hierarchical modeling. You can borrow information, you can put Bayesian distribution on random effect and fixed effect and quantify all of that components. So I'm just curious why you haven't thought about it, or that's what you mean by an opening research area, and that's where I think maybe more work. But from a Bayesian viewpoint, it seems to me that would be a very simple way to address that.
those are two great questions, and I have thought about both of them a little bit. So one is kind of in the cross-section settings, and this may be kind of more specifically in econometrics, but it's sort of the sense that when we're estimating standard errors, we don't really have to do a lot of modeling. Kind of we can sort of do that for free, kind of through bootstrapping or kind of through robust standard errors, and we don't actually have to make any assumptions there. We may not be estimating what we're interested in, but at least we can do inference for whatever it is we're estimating. And it turns out really that's not true in general, and you kind of do need to think about exactly where the variation is coming from, and you need to model that. You need to make assumptions on that. Yeah. So, this is on. Okay, yeah, sorry. So you do need to make modeling assumptions here, and I would be very happy to do that from a more formal Bayesian perspective. Partly here, I wanted to make this accessible to the people who are using difference in differences methods, and so I wanted to stay closer to my reading of that literature and what would be effective in communicating with them. But sort of once you're forced to make modeling assumptions, doing that from a Bayesian perspective would be a very natural thing to do.
Yeah. Well, you can always be Bayesian on parametrics too.
Yeah, but again, sort of why is the difference in differences literature so popular in the empirical literature? It's viewed as very simple and very transparent, and so even though I feel,
I agree, transparent.
but at least apparently it's viewed as transparent, and so I think there's a lot better methods out there, and it doesn't make sense to me how popular it is, how widely used it is. But and so it's a challenge to get people to do different things, and so there's challenges in the communication.
My point is, you can still have a difference in difference and specify that model, but then do the Bayesian approach to the variance.
Yes. No, and so I would be happy with that, and I see this essentially kind of close to that, because once I've specified the model, I'm not super worried about the importance of the prior here, and so I would be happy to kind of view it as a more formal Bayesian thing. But I also want to come back to the spatial, the comments you made about spatial correlation. I think I felt for a long time, when I was at Harvard, we would just never have in the econometrics seminar presentations about spatial correlations, and people, this sense in much of the empirical literature, at least in economics, the correlations kind of would be taken account of by clustering, kind of by state, as if these correlations are only within states and stop at state boundaries. And there's that's obviously not true. Kind of we see a lot of both policies and outcomes that are correlated spatially, and not just kind of in terms of distance, but also across the country. In the end, the East Coast and the West Coast move much more similarly than many of the states in the middle. And we don't really have very good ways of doing that. I mean, some of the spatial literature is very much the focus, sort of drawing on earlier statistical spatial literature, where it's all distance-based and kind of trying to predict outcomes locally, but it's not really taking account of the type of settings that are relevant for social sciences. And I think we need to do much better there. There's just a lot of interesting questions, because estimating a correlation, full correlation matrix, you need to put some structure on there. So you need to find multiple outcomes as a way of building, of kind of showing that there is a strong correlation between what happens in New York and California, but not necessarily what happens in New York and Kansas or somewhere else in the middle. And so building good models for that, I think that's an area where we need to see a lot more work, and I think that would be incredibly interesting.
Thank you. Jali.
Thank you, Guido. Just to show that not everyone from Harvard is Bayesian, I'm going to disagree with Francesca. Well, actually, I think the real issue here, I think you cast it as the validity and the power, and I wonder if it's better to emphasize it's an issue between marginal validity and the conditional validity. Because the word's validity made our people say, oh, it's valid, but it's actually not, right? Cox's example showed clearly it's conditionally. And for practical purpose, at the end of the day, all we care is does it work for my case? It's not some average cases, right? So I think maybe better to emphasize the conditional validity was when, and that's actually where the Bayesian frequentists start to have the big problem. I mean, you know, I'm as much as the Bayesian as anybody else, but I also understand the Bayesian's really, it's a shift to the, what I call is the leap of faith, right? Frequentists do everything on average. In the end, you interpret the average results as what you want for the particular one. Bayesian shifted the leap of faith at the very beginning by setting up a pri, which takes care of all the conditioning, everything. But in the end, the pri, particularly with these high dimensional problems, is very problematic, right? And there's tremendous evidence. So I think by thinking about these conditional validity is like the traditional, right, conditional relevance set, that kind of thing, right? But the other question I have is that, is there some kind of, you know, just by looking at the difference between the variance, the marginal variance of the variance and the conditional variance of variance, if you have these data, would that be, you still be able to establish some kind of hypothesis testing to test if there's nothing going on, right? Because there should be some information. If there's no difference between these two, probably, so some crude screening process, I don't know if that could be formalized.
Yeah, I agree with kind of with all those comments. I mean, I agree with the labeling, and it's, you know, in the end, it's sort of clear that we need to have some conditionality, that we have some conditional validity here. And yes, and I think you can do some of the screening you described. Yes, I agree.
Okay, Linda Valeri, I think, and then Giovanni Mellace and Koske.
You have to say what the Bayesian frequentist is.
Well, trained as both frequentist from my PhD advisor and then Bayesian for my postdoc, so I get the best of both worlds. So I'd like to ask two questions, one regarding the estimation, and in particular, like in my work, I encountered the issue of non-stationarity in many of the effects that we study. So we started thinking about considering using state space modeling for like synthetic control modeling, for example. But I worry about overfitting there, so I wanted to hear your thoughts on that. And yeah, like a practical example on this, for example, we have data pre, during, and post-COVID, and we see that effects might be different due to this particular shock, but also, so it also could be, you know, for something exogenous that happens, but could be also something endogenous. So within people, like, people are, have different experiences in life or like periods of life, and within their life, the effects, treatment effects might be different. So talking about non-stationarity and ways to deal with it. The other question is regarding the variance in terms of when your data is imbalanced with respect to N and T. So for example, when we use wearable devices, we have like a high dimensional T, but might be very low dimensional N. If I say I could have like daily data for 6 years for only 10 people. So in this case, how does your like, you know, how do you think the problem of variance estimation is gonna change, you know, whether you would lay more on the, you know, time versus unit, and so this is my two questions, thanks.
Thank you.
Yeah, kind of starting with the latter, I mean, I sort of feel, I think this may reflect more on the econometrics literature, that people have been trying to kind of find general methods that are going to work for all these different settings. And for the panel data literature now, it's clear there's a lot of settings that all fit into this general framework, but that are very different in practice. And so the cases you described where T is much, much bigger than N, and there's some other cases where N is much, much bigger than T, don't necessarily suggest using the same methods in particular for inference. So I think we need to get a range of different methods that cover all these cases and that are going to do well, at least in some cases. And then the earlier part about the non-stationarity, Yicheng Xu also has done some work kind of showing that in a lot of these settings where people have applied synthetic control methods, they're using data that have a huge amount of non-stationarity. And that's clearly affecting the properties of these methods. But the methodological literature hasn't really engaged much with the time series properties of these settings. You can sort of see that in the characterization of these synthetic control estimators as just regression estimators, where you use the time periods as the observations. But typically, we kind of think of regression analysis as being applied to exchangeable units. And if we do have these strong non-stationary components there, we need that's going to affect how well these methods work. And so we need to pay more attention to those components. And some of these state space models, kind of the Brodersen et al. Work as well, is very interesting in that regard. But I think there's still a lot more to be done there.
Thank you. Can you please pass the microphone to Giovanni Mendace, head here, and then Koski Imai.
Thank you. Very interesting talk. So you mentioned that basically using observation which are further in the past is problematic because probably they don't have a lot of predicting power for imputing the outcome in the post-treatment period, right? But then don't you also have a similar problem when you move back from the treatment period and you estimate long run, let's say, treatment effect? And how should we adjust inference to take that into account? Because our prediction is going to deteriorate the farther we go from the treatment date, right?
Yes, I mean, it's sort of clear that when we're using all these methods to predict many periods ahead, the inferences are going to be increasingly unreliable, and a lot of the current methods don't really fully take that into account, because again, they kind of just treat the time units as the time periods as exchangeable, and it doesn't really make sense. You would like the confidence intervals and the measures of uncertainty to reflect the fact that we're really not very sure about the predictions more than a couple of periods ahead. But you're absolutely right there.
All right. So, Koski Imai over there.
Thanks, Guido, for inspiring talk. So I really like the point about, low quantum exchangeability is problematic. And I was thinking, one of the things that's also being missed in DID panel type of literature is the, spillover and carryover effects. So not just the sort of, just the dependency in the error term, but the fact that the previous treatments are affecting the future outcome, and also, cross-sectionally. So the units who receive the treatments may also affect the other units, maybe in the future years as well. So I wonder if you thought about that, or that seems to me like one of the even bigger problem of the current literature. Those things are assumed away. So.
Yeah, I mean, certainly kind of the spillovers over time is an issue that's sort of curious in the sense that the 90s literature in econometrics, kind of the Blundell-Bond, Ariano-Bond type modeling, was very cognizant of these dynamic effects and paid a lot of attention to that, and somehow that has disappeared from the current literature, and I don't know why, and sort of have this recent survey with Dimitri where we lament that that omission from the literature, and I think we need to go back and take that into account. Now, because in some cases, that particular the concern about dynamics may only change the interpretation of estimates. Kind of in some of the synthetic control applications that Alberto Abadi and co-authors worked on. If there's just a single unit that's being treated and it's being treated from a particular time onwards, it's changing the interpretation of what you're estimating, but it's not going to change necessarily much of how you would be estimating things. That's not the case for the spillovers, the cross-section spillovers you mentioned. And like Francesca's comment about the spatial interactions, I think that's a hugely important thing. And in much of the empirical literature, there's kind of the sense that we take account of that by just using the right level of aggregation, and then we don't need to worry about that anymore. And these spillovers are clearly much more complex and require much more careful modeling than what's being done. And I hope kind of that the literature kind of using panel data, this type of data in the future is going to pay more attention to that, because it's clearly important in practice.
All right, thank you. So, first, Eugenio.
Hello. I have a question about the assignment mechanism, because in a panel data setting, when you have a time-varying treatment, which could be binary but also continuous or other kind of response, there are many strategies to deal with this problem. Mostly G methods and weighted schemes. There are many ways, but it's not clear which one is better and when it's better to use one over the other. Also, I especially want to know what you think it's interesting to do more in this direction. What could be done more about dealing with the assignment in a time-varying framework?
Yeah, I mean, that's sort of a tricky thing. It's sort of one thing to say, well, we want to do this for general assignment mechanisms, but in practice, there's a bunch of special cases that are really very common, and so we need to take account, we need to make sure that things work well in these special cases, and that includes kind of the staggered adoption case, but also includes cases where there's just very few treated units and where it's going to be very challenging to really build a credible model for the assignment mechanism, because we just don't have a lot of data on the assignment mechanism to help us build good models there. And so I think one of the things that's going to be important in this literature in general, sort of like in much of the machine learning literature, people have built these data, have constructed and posted these data sets that we can use to kind of test out these methods. In these settings, we need to have both data sets and data generating mechanisms so we can actually test kind of whether particular methods work. Just having one data set is not enough. When we're interested in these causal questions, we need to be able to repeatedly generate data that are realistic and that correspond to the type of things we see, and then we're going to be in a better position for actually seeing which methods work well in what type of settings. And there's a little bit of tendency when people come up with new methods kind of to show that they're working in a particular setting, and it may be a very stylized setting, but it would be helpful if people showed more kind of where these methods break down, kind of what really the range of settings is, where they are appropriate and where they stop being appropriate. And I think that's kind of where the assignment mechanism plays a big role. In the earlier literature, people would just condition on all the exogenous variables and they weren't really paying attention to the patterns there. But if you're in a situation where there's just only one treated unit, you're going to be very limited in what you can actually do. But that's a very important case, kind of as the synthetic control literature has shown. You see a huge number of applications of these methods precisely because that's such a common situation. So we need to understand what's going to work well, what's going to be effective exactly in those settings.
Perfect, thank you. Dimitri here, and then over there.
Thank you, Hidam. This is the second time I'm listening to this, so now I have a question. So when you think about exchangeability in the first part, right? So do you think of this, and kind of when we think about it, it's of course striking, right, that we can just permute or forget the labels, but should we think of this as a sign of, like, there is some sort of misspecification going on, we should consider a more flexible model, or it should be a sign of efficiency problem? Kind of we are using a model that's flexible enough. Partly, that's why it's exchangeable, right? We condition on the time patterns, so we don't need to model them. And that's why we kind of think that's fine. But then, kind of when we do analysis, we want to take a time series component into account. And then, kind of, I think that's different, right? Because it's the first one, and it felt like to some extent that was the first one, right? Because we were changing our estimator, kind of doing this more flexible weighting. That's one thing that we should do, but if the second one, then it goes back to the variance analysis, right? So then we need to estimate the variance, understand the properties of the errors, and then probably take that into account. So the question is, how do you think about that? Is it too simple, or is it not simple enough, the model?
No, I think the model is too simple. We're trying to come up with the best prediction for a counterfactual outcome, and we're not using the available information effectively. We're leaving some information on the table. And so we need to build better models there.
Okay, so the point is would be that we probably need to consider some dynamic models in the outcomes, okay? And so that would go back to the panel data literature that does that. Okay?
Yeah. Thank you. So Andrea, and then Andrea Hino, yes, and then Marika Valen. No, please, Andrea.
Okay. So maybe this is more a question for the round table, but let me ask you now that we have time. So the introductory statements to this conference emphasize the interdisciplinary nature, but if I look around and I'm not mistaken, I don't see macroeconomists. And
I miss them. I missed inviting them.
No, but look, if I look at what Guido said with the eyes of my colleagues in the macro section of my department, and I read things like row column exchangeability is not a good assumption, the time dimension is important, well, I would say we knew that. That's exactly why we answer your same causal inference question with completely different methods. We do theoretical models, where theory here means economic-based theory, no? And this gives restriction.
Oh, there is a macroeconomist there, actually. I missed
so maybe you can make the statement
Alex,
better than me. Oh,
Alex,
you can do that. But
it's
anyway,
not true,
the question is, are you moving in this direction with this lecture by emphasizing the need of more structure with respect to what we usually do? And more generally, and this is really the next round table, but how do you view the relationship between this field that is almost missing here except for Alex
Ludwig, yes.
and that, in fact, for all of us who live in departments in which we interact with these colleagues, and sometimes we also appreciate, often we appreciate what they are doing because they are really inspiring work. So I would like to know what you think about this, also with respect to the question of counterfactual exercises, which I think they can do, and it is harder for us to do them.
Thank you.
So I'm very sympathetic to bring in theory there. I mean, so there's a couple of places where I see some of that happening. One place is in experimental design. There's a lot of experimentation going on in the tech companies where they're doing this in marketplaces. And so there, to do effective experimental design, it's very different from the traditional biostatistical settings, kind of where you have bunch of individuals and you treat some, and you put some in the control group, and they don't really interact. The experimentation in these tech companies happens in marketplaces where you have different sets of units of individuals interacting, and the experimentation you do changes the equilibrium, and so you need to actually take account of that. I mean, Stefan's been working on that in particular settings, kind of where you really explicitly take account of the new equilibrium that arises as a result of the experimental design. And so there you need to bring in economic theory, not necessarily very relatively simple theory, but you do need to think about supply and demand and equilibrium. And so I think it's very important there, and it's very important in some of these other settings. And I think there's a lot of macroeconomists who are taking the causal issues much more seriously. I really like the work by people like Emi Nakamura and John Steinson, and so I think these literatures are converging. I mean, I spent part of my time in the economics department, and even at the business school, I have colleagues in macro whom I think are doing very interesting work in that regard. I think causal inference is in the end very much an interdisciplinary enterprise, and so it's great to kind of have the interactions with the computer scientists and the statisticians, as well as all the social scientists, because the political scientists are doing really interesting things in this space as well, and different parts of economics. And so that's going to be very important for moving the field forward.
Yes, have more. Yes. So I think we have Marika Valente and then the macroeconomist, Alex.
Yeah, so since Fabrizia said to be provocative, I join Andrea in a provocation. Very short. So you were talking about the importance of controlling or matching in a good way on the pre-treatment outcome lags rather than the far away. But why should we care at all about controlling for the older pre-treatment lags and instead focusing on covariate, right? So we all want some covariate balance as well, or controlling for a decent number. And we know that we cannot do both, right? We cannot control for a large amount of pre-treatment lags and covariate. So, you know, what's your take? What's your stand?
Yeah, so because in part of the literature, kind of in part of cross-section literature, often we use lagged outcomes kind of just as another type of control, but we analyze them very much in the same way as we did other characteristics. I do think kind of the panel literature makes clear that lagged outcomes do play a special role, given that those are the things we're trying to impute in the future. They do have a very special role. They're very close in the end to future values of those outcomes, and so it is helpful to analyze, to give them a special role in the analysis. But you're absolutely right that given the type of data we typically have, where kind of both N and T are reasonably large but not very large, and so we're limited in what we can do, and we can and especially if we also have a bunch of covariates, we need to make some choices about how we bring those in. And so if in the end, kind of, again, to go back to one of the Abadi Diamond Heimüller examples, if I'm trying to predict the smoking rate in California in a particular year, the lagged smoking rate for a number of years, kind of seeing what that time pattern is like, is going to be hugely important there relative to, say, other characteristics of the states. And if I want to predict that, I do want to look for states that have similar patterns in terms of their smoking behavior, rather than, say, adjust for per capita GDP in these other states or education levels. I think the lagged outcomes are substantially more important in practice in doing these predictions. And so I do think they play a special role that is captured kind of in some of these models.
Good. So I think one last question from Alex, and then...
It's more a comment, not a question so much. So, Andrea, is it on?
I think it's on.
Andrea just unintentionally played a ball to me. I was not planning to speak up, but this is exactly what we did for some time now as complete outsiders to the literature, thinking about how do I identify policy effects in situations where economies over time follow particular paths. But we go a step further, we say it's not time that we should think about. It's the stage of the development of the underlying process. So we think about the simplest macroeconomic model, the solo growth model. If you have two outcome variables, then it can be at any different time, at a very different stage of the development process. So what our method does is to say, let's trace out this heterogeneity in stages first, and then this heterogeneity in stages gives us the identification of policy effects that may hit all regions at the same time period. And I think this applies to many, many macroeconomic contexts, and it's very much guided through this lens of structural modeling of macroeconomic developments, which I think plays an important role for, or should play an important role for identification in these contexts of panel data. Thanks, Andrea. This was unintentionally because you didn't even know that I was here, but I took this opportunity to speak up.
Okay, yes, you want to...
Yeah, I agree with that. I think it would be very useful to bring in more of that literature.
All right, so I think this was a very last question. Yes, no, that's okay.
Hi, thank you for the talk. So to end on a philosophical note, I'm just curious, and I always struggle with this when I'm doing panel data stuff. The sample size is so small, and how do we deal with generalizability? What is your advice in terms of like, when do you feel good? You know, ideally, how many times would you run this? But if it's a state policy evaluation, you really are only going to have one or two states who do something, and we're not going to be able to repeat it 5 or 10 years from now, maybe, but on the same state. So I'm just curious what advice you have when I lose sleep over that.
Well, yeah, I don't think it's... I try not to lose sleep over these things. It is sort of tricky kind of to think, you know, especially when we're trying to do these repeated sampling. Thought experiments kind of exactly what we should have in mind there. Because, you know, when we look at these panel data, say for the traditionally there were these methods a lot of these methods were developed in settings where the units were individuals, and you could very well imagine having different sets of individuals. But when we do this with aggregate units like states, it doesn't really make sense kind of to think of this being applied in other settings where there's multiple New Yorks and multiple versions of California. And you want to do this in a setting where actually the distances between the states are more or less stable. And so we really need to think about different ways of approximating there. And it's not clear to me what the appropriate way of doing that is, but starting kind of from a design perspective where you think, well, these states are what they are, but I'm changing the policies that I feel that makes it a little easier to think about what the uncertainty is we're trying to capture there.
Thank you. So, great. Thank you. So, we're going to have a coffee break now. We reconvene at 11:30. And of course, you can take a fresh air, take your coffee outside. Thanks a lot.
We should start. My name is Andrea Ichino. I am a professor in the economics department of the European University Institute, and I'm chairing the first round table of the symposium on causality in socioeconomic research that follows the inspiring lecture that Guido just gave us. And the idea of this round table, at least as I understood them, is to bring really into action this interdisciplinarity focus. Here we have two panelists in addition to Guido. One is Professor Miriam Golden from the European University Institute, a political scientist, and Dean Eccles from MIT, who is a professor in marketing. So here we have two different disciplines, and we will hear how they think about the topic of this conference and Guido's provocative statements with respect to their disciplines. So the thing will be organized in this way. They will have about 12-15 minutes each to give their comments, and then Guido will reply, and then we'll have question and answers by the audience until 1 o'clock. So, Miriam, you have the floor.
Thank you, Andrea. So when I was put on the program, I was, in fact, at the European University Institute. But as Andrea knows all too well, everything at the European University Institute is temporary. And so I am now in residence at Stanford University. And my affiliation with UCLA is lifetime. So I figured I'd keep it there, too. Thank you. I'll tell you something about how I think the potential outcomes framework and identification issues have penetrated political science. So I won't give too much of a substantive talk, but more, since most of you are not political scientists, I'll tell you something about the kinds of problems that we as political scientists have been able to work on using this new framework. So the political science baseline is very different than other disciplines. We are a very heterogeneous, fragmented discipline. We are not hierarchical. There are many centers of power, rival centers of power. It's a very feudal discipline. There is no shared methodological standard. And it is defined more by what it studies than how it studies phenomena. So political science, broadly speaking, is the study of politics, government, and the social and behavioral processes underlying them. And you could do that using various and arguing over them pretty much long term. So what has been the impact of what I'll call the identification revolution, or what has been called the identification revolution in political science? It establishes a shared methodological foundation that is extremely compelling and attractive precisely because it crosses many disciplines and allows us as political scientists to now converse with and collaborate with, in really meaningful ways, colleagues from not only economics, but also psychology and other social sciences. It has therefore been intellectually transformative, but I would say unevenly assimilated. By which I mean, just to give you an example, to the best of my knowledge, and there are people in the room who will correct me if I'm wrong, nobody who has come up for tenure in political science at the top 3 departments in the US, therefore in the world, who uses the potential outcomes framework and is not a methodologist, has been granted tenure. So it is very, very divisive in the discipline. But it has unleashed a methodological revolution that is really transforming the kind of work that we are now able to do. And it gives me huge pleasure to know that we have shared standards with economists and psychologists and I hope some sociologists, and that we can all talk about the same thing. So methods are now, I would say, the most exciting part of political science. And I point as an example, just to fix ideas, to the book by Graham Blair, Alex Kopic, and McCartan Humphreys called research methods, which not only offers a new tool called declare design for setting up your research design, but offers a whole, I would say, new way of thinking for, or implements a new way of thinking based on potential outcomes framework in political science that is accessible. So let me give you some examples of the kind of questions, the kind of work that has been done in political science using causal identification. There's been a wave of experiments, real RCTs on the ground. There's been hundreds of experiments on political participation, especially get out the vote work, which has been cumulatively extremely important. I have to say substantively it's kind of, I don't do this work, so I can say substantively it's kind of trivial, because obviously in the US, when you're trying to get out the vote, you're really working at the margins with, you know, can you get out another 0.01% of the vote? So it's substantively very small, but of course now with elections so tight, it's very meaningful. Another example of really innovative RCT work is the Medicaetta 1 study run by EGAP, which is a study set in 7 places around the world about whether giving voters information will change their vote and move their support towards better or less corrupt political representatives. That came out in a book, I would say, about. Their findings are that nothing you do changes how people vote, but that's a separate discussion, why information is not effective. So we have these amazing RCTs being done in political science. We have a lot of natural experiments also. Some of them use institutional discontinuities. I was hoping to see Tommaso Nannicini here to give him a shout out, because he's not a political scientist, but his work, I would love to adopt it in political science. He has done some amazing work using discontinuities, institutional discontinuities, including this paper about fiscal restraint and public debt in Italian municipalities that uses thresholds of under 5,000 residents and over 5,000 residents where the institutional rules differ. There's also a lot of work on geographic discontinuities. I don't know if my colleague Elias Dinas is still in the room, but Elias has done some amazing work on geographic discontinuities, and my former colleague at UCLA, Dan Posner, did a path-breaking study of whether public policies exacerbate or diminish ethnic conflict, looking at tribes across African borders, which has become a very kind of standard source of geographic discontinuity. Finally, we have what I'll call quasi-experiments, which are settings where political scientists use D&D. So effects of recentralization of fiscal authority in some parts of Vietnam on public service delivery. That's a pretty well-known study. And then I have been working on a paper using Kosuke's panel match, which is a staggered D&D to study whether civil service reform in the across the 50 U.S. states over 120 years increased re-election rates of legislators to state houses, and it has a massive effect of like 10 percentage points. So there's lots of things we can learn that we really were not able to study very effectively before using these new methods. So the conundrum for us, however, is that, and the main objection to the use of the identification revolution in political science is that it flattens the range of questions we can ask. There are, let's say, the most major questions that we traditionally study in political science are not very easily identifiable, because fundamentally what we care about are big structures and political regimes. And so give you some examples of questions. I define them as not yet causally identified, but maybe they are not identifiable. I'm not going to comment on that. What causes the development and consolidation of democratic institutions? That's a really hard one to think how you would get identification on that. What causes the demise of corruption as countries develop economically? I've worked on that personally, really hard to get a handle on it. What causes democratic breakdown? In the US at least, and to some extent in Europe as well, everybody wants to know whether we're headed for a democratic breakdown, and very hard to know how you would do research that was well identified on that question. What are the effects of proportional representation compared with single-member district electoral systems on voter representation? You know, in the real world, randomizing an electoral system, you can't convince governments to do that. You can randomize, or at least you can stagger the rollout of specific policies, and governments are often willing to do that. You can partner with politicians to work with them on how they campaign politically, and many of them are happy to do that. You can partner with political parties. You can even partner with judges and courts to randomize various things. But I don't know of anybody who's been able to partner with a country to get it to randomize the electoral system just for the purposes of scholarly knowledge. Finally, what are the effects of presidential versus parliamentary regimes on democratic stability? That's a very long-standing question in political science, and we can't randomize regime type. Do one-party dominant regimes reduce political legitimacy? That's not, okay, so the highly exaggerated conclusion that I myself don't agree with is that we can only get precise answers to questions we don't care about. I don't think that's true in economics. In economics, you know, economists really care about a lot of very precise policy questions, and you can get precise answers to those. And to the extent that political scientists care about some types of policy questions, you can get precise answers to those. But the traditional questions that we ask in political science can't get precise answers to them. So we can't answer the questions we care about. And that is a conundrum. So as a political scientist, what do? We can either narrow our focus and only ask questions that we can answer, and that is a great way to go for some things. Or I'll make another proposal, like I think that sometimes we should ask theoretically complex questions and use multiple designs to identify subsidiary questions. Some of those subsidiary questions can then be answered using accepted methods of causal identification. And then we want to know what the preponderance of evidence says, and that's going to vary in strength across different subsidiary questions and methods used. So I'm going to give you an example before I stop from what I've been working on, because I'm really committed to trying to do causal identification, but I'm working on a question that I don't see how to do it, and so maybe you can help me. But here's what I'm doing. Why do re-election rates of national legislators in 100 countries, 100 democracies around the world rise very steeply with economic development? We cannot manipulate economic development. We can examine whether the same is true over time within subunits of a country. So as the US states developed economically, for instance, did re-election rates rise? Actually, yes. That requires the assumption that what happens over time within subunits is basically the same process as what happens over time in space in countries. That's a pretty big assumption, okay? But that's the assumption that you have to make if you use this other setting to make inferences about what you care about. If you go with that assumption, you can then transport hypotheses from the setting of like US historical development, states, to collect, for instance, interview data with legislators around the world, which I have done, where I talk to them about, hey, do you want to get reelected? Why? And of course, that's not causally identifiable, and they might be lying, but the point is really like, how does the evidence line up when you put all different kinds of evidence together? If we collect many kinds of descriptive data and some data that is identifiable, can we tell a coherent story that people will buy? Only fragments will be identifiable. Maybe, if I'm lucky, the whole will be greater than the sum of the parts. But this works only, I think, if you use the best available design and evidence, and I recommend structure all of it using a potential outcomes framework. Think about it that way, even when the methods you use are not methods that actually allow identification. And so I'm hopeful that this framework, this way of thinking, can be used in my discipline. Maybe it's a weak discipline, but there you have it. We're still paid by our departments, and so we have to keep going. You know, I am hopeful that we can incorporate and integrate these transformative tools without relinquishing the kinds of very complex questions that we want to ask in political science. Thank you.
Thank you very much, Miriam. This was really inspiring. And I think you said that this is a problem in political science, less so in economics. I think it is also a big problem in economics. So curious to see what the other panelists and the audience will say about this. But now we move to the comment of Dean Eccles.
Yeah. Yeah, sure. Hi. Really, it's my pleasure to be here. So, and to kind of initiate some of this conversation. So, this title isn't necessarily exactly what I was going to talk about, but it's sort of much of it. So, I'm faculty in. I'm a professor of marketing, I think, as I was introduced. And so exactly what does that mean? Well, one of the things is that I've been very interested in processes by which ideas and behaviors spread, and that's often been in networks. So a lot of my research, both methodological and substantive, has been about things like peer effects and spillovers and contagion. But what I wanted to comment on a bit today, I think fits with some of these questions about what's possible, in the potential outcomes framework, what's that's most suitable towards, and then also some of the kind of time series questions that were raised and some of the questions about spillovers that came up earlier. So I was going to say something about kind of dynamic and cumulative effects, using as an example some interventions on social media, talk about some combinatorial treatments, thinking about the cases where there's spillovers in a networked setting, and then cases where maybe there's sort of underdefined treatments in some sense, where we might actually want to know about the effects of network structure, but it's unclear exactly what we have in mind, right? So this is kind of the picture that we're like really familiar with from a potential outcomes framework, right? That we have these 16 units, and they all have something they would do under treatment and something they would do under control. And then, if we run a randomized experiment, we reveal some of those potential outcomes. We get half of the potential outcome table. It's supposed to be in there. Oh, I think maybe I cut that slightly incorrectly. It's supposed to be a different clip of some video. But anyway, I think what's maybe a little bit more difficult is cases where things are evolving over time. And so one example that has gotten a lot of attention recently is ways that algorithms and affordances of social media might be affecting political polarization. A lot of my work has also connected with political science as well. So, so I think, now last summer there was this series of papers published as part of a large collaboration between researchers inside and outside of Facebook, and this is how Science summarized a bunch of that, wired to split, right? And so part of the idea there was that maybe, we've seen this dramatic increase in affective polarization in the United States and in some other countries over the past decades. And so people have wondered, are social media algorithms contributing to this? And I think in some sense this is clearly a causal question. It's a little bit tricky to think about this and is very much just these kind of potential outcomes, two pairs of potential outcomes, right? Because we're not necessarily thinking about exactly the idea that social media either exists or doesn't exist, and in this sort of one time period, we're thinking potentially about accumulating effects over time, and we might be thinking about a whole rich set of affordances or characteristics of social media. But, looking at this, it's pretty obvious that, there's this increase, and, you can kind of see where Facebook launched in 1995. Facebook did not launch in 1995. That's a joke. Right? So, so what did these folks do? This is research I'm not involved in any way. I'm just kind of commenting on this as an example. They ran these randomized experiments where they had a control group, and then they randomly assigned users into different changes to the affordances of social media, like giving them a chronological rather than ranked feed, removing content that's being reshared, which you might think is things that are particularly inflammatory, and that kind of contagious potential of social media might be one of its main affordances that could promote polarization, and also sort of downranking like-minded sources of content, which you might think could promote a filter bubble, et cetera. So here's one of the summaries from one of the papers. Contrary to expectations, the treatment does not significantly affect political polarization or any measure of individual level political attitudes. This is from one of the papers that was about removing reshares, but basically all the results in all the papers are null for these outcomes, right? So I think that's kind of interesting. Now, does that tell us about the original question, which was, this increase in political affective polarization that we've seen over multiple decades? Does this mean social media contributed nothing to it at all? I think there things are a little bit more, more ambiguous. And so one of the ways that I had thought about this was that will help bring out this kind of dynamic question is actually before these papers were published, I knew that they were doing these interventions, but I wasn't involved. And so I thought I would predict all of the treatment effects to sort of get a sense of, what if I was an expert in this area, what did I already know, and should I be updating from these? One of the tools I used in predicting the treatment effects was some of the leaked Facebook files from Frances Haugen, one of the Facebook whistleblowers. She leaked this document to US legislators. And so this was an earlier experiment where Facebook had internally turned off their ranking and put in place instead chronological ranking. And so I looked at the results of that, and one of the things that showed on a behavioral outcome was that, if you turn off ranking, as you might expect, people spend less time using social media. You've just made social media worse, right? And so, the top line outcomes in the experiment after 10 days, time spent seems to be dropping without hitting a bottom yet. Okay? So, interestingly, actually, revenue was up over this time period. You can reason about why that might be and what that reveals about actually the preferences of social media platforms, okay? So I tried to use this information in making my predictions about what was going to happen, especially to some things related to, how much people's time spent on social media was going to drop, and also some of the outcomes that I did expect would be affected, and which were actually, like news knowledge. People get news from social media, so if you make social media less useful, they use social media less, and then they're less well informed about the news. And that's one of the things that actually did happen in all these experiments. But I ended up being wrong about some of these things. I underestimated how much time spent dropped over this time period. Now this isn't time spent over this period, but this is this period that they ran these experiments in right before the 2020 elections, and there are 3 different survey waves. So this ends up being, you know, a multi-month experiment, but the survey waves that are measuring the outcomes, like political polarization waves 3, 4, and 5, these were sort of averaged together. So you can think about when they're estimating treatment effects, it's sort of on average treatment effects of like a month and a half of this treatment, okay? That was longer than the 10 days that I had used there, right? And we had seen that, hey, it's dropping without hitting a bottom yet, right? So there's something really dynamic going on here, and that's part of what made me end up making some mistakes in making those predictions. If you want, you can find online where I wrote up all my predictions and which ones I got right, etc. But, you know, one of the things that was hard to anticipate was the dynamics of this. In a lot of ways, the analysis didn't allow looking at dynamics, right? I think this is, of all these different papers published in Science and Nature, this is one of the few plots where there's anything like a time series happening, right? And there was nothing about the design that was conducive to picking up on these dynamic effects. So I think if we were to take sort of more seriously the time series nature and also the dynamic accumulating effects of treatments, and we wanted to answer questions about what's the effect of social media over a longer period of time, we might need to think about that. Okay. So more briefly, I want to say something just about combinatorial treatments, right? So the picture we looked at before, that table, you know, just had treatment and control. Every unit is affected by its own treatment. But a lot of times we're interested in treatments in a network setting. Certainly you could think about that in the context of the effects of social media, right? It's not that just reducing, you know, your own time on social media or your own algorithm is the same as reducing everyone's time or changing everyone's algorithm, right? So that the experience of a particular person in a network could depend on their own treatment, the treatment of their neighbors, and maybe actually over a longer period of time, especially the treatments of people far away. So what does this look like when we try to use the potential outcomes framework to think about this? Well, instead of having this table with 2 columns, we have a table with another number of columns that's potentially like, you know, 2 to the n. For every possible treatment assignment vector that the n units could receive, there's some potential outcome for every single unit, right? Okay, so this is then a table that has n rows and 2 to the n columns, and we get to see exactly 1 column. And we're going to want to learn something from seeing this 1 column, right? We might want to learn, you know, in some of my methodological work and a lot of applied work in the tech industry, people are interested in contrasting outcomes under total control versus total treatment, some kind of global treatment effect, right? But there's all kinds of other things we could be interested in here. Actually, one of the problems, I would say, is that when you're facing this world, not only is it unclear if things are identified or how to estimate them, it's kind of unclear what you want to estimate, right? There's just an absolute explosion of possible estimates. And I think actually the methodological literature in this area has, you know, had a lot of similar but kind of different estimates, and it's unclear how to decide among them. I guess one of the things I might suggest is that this is a case where sort of grounding things in real decisions, what are the decisions that we're trying to inform, can be helpful, which is why it's very natural that you might want to compare the all zeros vector versus the all ones vector. But there's other things that could also be decision relevant there. Okay, finally, I want to talk about actually effects of local network structure, and this is a case of where people sometimes have underdefined a treatment. So a lot of the time I've been interested in effects occurring on a more or less static network, or a network at least we're conditioning on in some way. So people are being affected by their peers, but who their peers are isn't sort of changing on the time scale that we're interested in, right? But where do people get their network neighbors anyway? Where do people get these network structures anyway? And there's this really rich literature in sociology and related areas that the types of ties and types of network structures that we have around us could be particularly influential, right? And so, and we might ask questions not just at the ego level, like, hey, is this person in gold, are they better off than the person in red? Maybe because they have this long tie that's connecting them to an otherwise distant part of the network, giving them information and opportunities that would be hard to get from their local network. But we might ask questions globally about, hey, is this network on the left or this network on the right? Is that going to be more conducive to the spread of information, more conducive to the spread of a product or a new norm. And so, you know, those kinds of questions, we then want to say something about what is the characteristic of the network that we're trying to pick up on? What is that treatment? And so, just as an example, in some of my work, we focused on how many long ties individual people have, where long ties are ties without mutual neighbors. So this, for this focal individual in blue, this is a long tie in that they don't have any mutual neighbors with that individual, right? And we might think that those long ties are particularly advantageous as sources of information. So we released a bunch of data on this about at the zip code level in the US and Mexico. So there's a bunch of, you know, interesting kind of spatial structure to that. You can look at things like something happened in Mexico here. You can look at how, say, this fraction of long ties is associated with something like median household income. It's highly associated with it. I'm not going to say that this is a simple causal relationship at all. But I think it's interesting to think about how do you actually do causal inference about these kinds of effects of network structure. We've chosen one summary of this really high-dimensional object that is somebody's ego network. And so how should we go about trying to do causal inference there? Here we have a lot of problems. You know, we have a bunch of simultaneity and kind of there's causation in both directions. Not only might be people benefiting from having these more open network structures, but you know, you might get these more open network structures by being in certain types of professions. You might be able to maintain certain types of network structures by being wealthier, right? But even in cases where people have used experimental variation, so here's a summary of a bunch of experiments from LinkedIn in people you may know work, and Iav is one of the authors of this work. They took a whole bunch of cases where LinkedIn is recommending people different sorts of relationships, different people they could connect with on LinkedIn, and said, let's treat these as instrumental variables for how many different types of ties people have, and see how those ties that they have affect what job changes they have. Okay. But and I mean, they conclude moderately weak ties measured by mutual connections created the most job mobility, right? But this is sort of really depends on the specification of exactly which sort of these mediating variables, which of these endogenous variables describing people's networks we've included, right? And if we've specified that, how do we actually interpret these quantities? And so to me, it almost feels like there's this kind of under-specification of exactly what the treatment is. And again, I might, and this is just sort of where I'm thinking currently, I might really think that decisions could be an important lens here. Thinking about exactly what decisions we or individuals might make based on these kinds of estimates could help us figure out what we should be estimating in the first place, right? So, because I think without thinking about it, you can read to informing some very weird decisions. Like, if we conclude that it's better to have these long ties rather than to have a highly clustered network where all my friends know each other, it seems like the way to improve my economic outcomes is to get my two, best friends to have a falling out with each other, right? But somehow that's not what we have in mind, right? And so, but thinking concretely of what are the actions that individuals would take to intervene might be a way of focusing all of this kind of explosion of estimates and kind of lack of clarity about what the treatments are. So that's all I wanted to say. Thanks a lot.
So thank you very much. Guido.
Yeah, thanks, Miriam and Dean for these very interesting comments. So there's a lot of different things that were raised. And so I'm not going to comment on all of them, but I do want to make a couple of comments. Kind of one is that from my perspective, the interdisciplinary nature of the causal inference research is just hugely important. It's just really important to have these interactions between the different disciplines. If I kind of reflect on kind of some of the developments in the last the 3-4 decades, those interactions have between the different disciplines have clearly been very important. Think about regression discontinuity designs, which were developed in the psychology literature in the 60s, and just didn't really have much of an impact in other social sciences till at least in economics, kind of till the early 2000s. And it's hard to imagine now kind of that type of methodological innovation not spreading much more quickly because of conferences like this, because of the regular interactions we have between the different disciplines. And there having common language or multiple common languages, but having ways of actually effectively communicating is just very important. I remember kind of in the early 90s when I started working with Don Rubin, a huge part, the huge challenge early on was kind of just establishing what we really meant kind of by when we thought about what were effectively very similar problems, but problems we thought of in a very different way. And kind of there, the focus of different disciplines on and different perspectives can just be a real challenge. When I've worked with some of the tech companies, at times I've discussed kind of how to do demand estimation kind of with computer scientists. And from an economics perspective, it's very clear that you don't estimate a demand function just by comparing sales when prices are high with sales when prices are low. You don't think of prices as being randomly assigned, kind of even after conditioning on other things. But for computer scientists, that's not the way they think about these problems. And so from their perspective, they see it as a prediction problem. And so they try to predict sales as a function of prices. And if it doesn't go well first time, you put in more stuff and you build a more and more complex model. And the idea that you would actually start by thinking about how prices are formed and what the market looks like and where the equilibrium prices come from, it's just a very alien thing from their perspective. We do need to have these interactions to make sure that the approaches in these different disciplines at some level internally consistent there. And so I think it's incredibly helpful to interact with these people, with the people in computer science, in political science, in statistics, kind of to benefit from the insights in these different areas. Now, kind of Miriam put me in this uncomfortable position where I have to sort of defend what people do in economics, which is not typically something I would like to do or I'm inclined to do. But I do think so. I do want to make a couple of comments on that. Because a long time ago I had some exchanges with Angus Deaton where he was also arguing that experiments actually weren't all that useful, they weren't really the gold standard, and they weren't answering all the questions that we were interested in. And of course, the latter part is definitely true. In economics, there's also lots of questions that we can't answer using experiments. We can't, when the Department of Justice is thinking about approving mergers or acquisitions, we can't do experiments there. These are one-off questions. These are causal questions. They're in the end kind of assessing what they think is the causal effect of allowing a particular merger to go ahead. And I think it's still useful to think of that from a causal or from a potential outcome perspective, but you can't analyze it by comparing a bunch of mergers, outcomes after a bunch of mergers with outcomes after in times where you didn't allow the mergers. These are all kind of unique, very different settings. But it is still useful to think of the causal nature of these questions and kind of think about which components of these models you may actually be able to validate credibly and effectively using the causal inference methods. And for example, for these questions of mergers or acquisitions, often the results depend on what the supply functions look like, what the demand functions look like, and you may be able to to harness experimental evidence or natural experiment type evidence to see what those are like and get credible estimates, at least of components of the model that feed into the answers. And I totally agree also there with Dean's comment that it's helpful to think about what the eventual decision problem is that you're facing. Sort of working with some of the tech companies in recent years has been very helpful in kind of seeing how they approach problems there, where ultimately they're trying to make decisions and they understand that they're not going to get all the components of those decisions right, but they like to have these decisions be informed by the data. And a big part of that is that for components of these questions where you can do experiments, it's very helpful to do those experiments and bring in that evidence. And so the experiments may not answer fully, may not be fully determinative of what the best decisions are, but they help you make better decisions. They give you information that feeds into those decisions in a way that on average, in the long term, is going to lead to better outcomes. And again, sort of, I want to push the view here that what the experiments do is give you valuable information of a particular type. Kind of, there's this whole big complex world out there, but there's a lot of different mechanisms playing a role. But experiments allow you to focus on particular components of that mechanism and get credible answers, not always precise answers. It's hard to do well-powered experiments, but they potentially get you precise and unbiased answers to components of these problems. But in many, sort of, as an example of settings where experiments are not going to give you the full answers, is in these settings that Dean also raised with networks and with spillovers. Once we have spillovers, experiments are not directly going to answer the questions you're interested in, even if you articulate them well, even if you focus on the average effect of exposing every unit to a treatment versus exposing no unit to the treatment. You're going to need some structure on the spillovers in order to make a lot of progress. Absent that, there's only very limited amount you can actually learn. And so in many of these cases, we're going to need, and it goes back kind of to some of the earlier things that Andrea Aquino also raised, we're going to need to combine modeling assumptions, economic theory or theory from political science. We're going to need to use substantive assumptions about the processes, about the behavioral models in combination with good causal evidence on other components to get to the questions we're actually interested in. And in the spillover case, that's sort of very clear. We need to put structure on the nature of these spillovers. And sometimes that's easy. Kind of sometimes we think that the spillovers are limited in a very particular way. In educational settings, we may think that the spillovers are limited to classrooms or limited to schools. In other cases, we may think that the spillovers are mediated by the network, and we may have good measures of the network. In other cases, sort of in online settings, we may think that the spillovers are mediated by particular summary statistics. In a case of Uber and Lyft, spillover, sort of my influence, if I'm requesting a particular ride, my influence on other individuals comes through the fact that I increase the competitive pressure on the drivers. But it's a sort of anonymous type of spillover that is mediated through the particular structure of the algorithm. And so we need to use that type of information to extract these spillovers. But that's clearly a very exciting area where I think there's a lot more interesting questions. A long time ago, I spent some time thinking and did some work on this, motivated partly by the school my kids were in at the time, where for the grades they were in, kind of first and third grade at the time, there were 2 classes for every cohort, and every year the school would actually rearrange these two classes. And it wasn't really clear exactly what their objective function was, other they were sort of trying to improve the outcomes for the 2 classes as a whole. And they thought kind of by putting some kids in the same class and some kids in different classes, they could improve, in some sense, the average experience overall. And so both the school and the parents were very interested, were very vested in this process. The school wouldn't tell the parents what they were actually doing, what they were trying to do, other than, and the parents kind of would say, well, I want my kid to be in the same class as this kid. I don't want them to be in the same class as this other kid. And it was all very complicated, and there was very limited information. But it was sort of clear that both the school and the parents thought it mattered a lot which class the kids were in. The interactions mattered a lot. And it was an interesting experiment that was done later by Carol Sacerdote and West, where they did this experiment at the Air Force Academy, kind of where they have a cohort of students coming in every year, and they put them in squadrons, where almost all their interactions in their classes are with people in the same squadron. And so the Air Force Academy can't necessarily change the distribution of characteristics of the incoming class, but they could decide to put them together in squadrons in different ways. They could put all these students coming in there are very good, but they could rank them based on prior test scores, and they could put all the smartest kids together and all the medium kids together and all the worst kids together, or they could mix them up in other ways. And what Carol Sacerdote and West did was very interesting. They estimated a model about the spillover effects for these students, and then based on that model, they tried to figure out what the optimal allocation was that would optimize some average test scores. And this because other things the Air Force Academy was interested in as well, dropout rates in particular, and there's other things, and there were, of course, constraints. They wouldn't want to segregate the squadrons by gender or race, but kind of within some constraints, they could allocate these. And so they actually estimated this model, and then they put together, they figured out what the optimal allocation was according to the estimated model, and then they implemented that, and it turned out that it actually did worse than random assignment. It turned out the model was too parsimonious, basically too linear, and it was important for the students to have students who were better than them, but not too much better, because then that limited the interactions, that seemed to limit the interactions in a way that made the overall outcomes worse. But so it's clear that kind of modeling these interactions and spillovers is very complicated. Doing experiments to get to the right decisions is very hard, and it involves a very intricate dance between the modeling and doing experiments to kind of get particular parts of the model nailed down very well. And so I think that's one area where there's clearly still a lot more work to be done. And of course, that's the type of thing where sociologists have a lot to contribute to the substantive questions, and political science has a huge amount to add as well. So where, again, the interdisciplinary nature is going to be very helpful. So let me stop there. And
thank you very much. So lots of problems on the table for us, for those who do causal inference. I think one positive news, if I can find a positive news in all the problems, is that I think we all agree that the potential outcome framework is fundamentally, is really important and useful, even in the cases in which we cannot empirically do a randomized control trial or have other kind of experiment or quasi-experiment. So at least this is a good news. It's important, and I think even macroeconomists now are starting to use it, even if they then shift to other methods. But I think there are two other elephants in the room. Even in cases in which we can do a randomized control trial or have other identification strategies, there is a problem of external validity that is often posed to us, to me, when I do my own research using this type of method. And the other problem is general equilibrium effect. As economists, we tend to think that if you do a treatment on a small scale, you may estimate maybe precisely the causal effect, but then when you extend it, you need to incorporate general equilibrium effects. And it's hard for me, personally, to think about how to do that without a theoretical mode. I just started with two questions, basically raising these two problems. But I think the best way to proceed would be to see if there are other questions and then give again the floor to our panelists. And they will pick whatever has been said for their own final remarks. So is there anybody who would like to ask a question? Okay, many. So let me start here.
And maybe I'll just respond to what you just said.
Sorry?
I'll just respond to what you were just saying about the general equilibrium effects. I think, which is related to what we were talking about with spillovers, but in some ways, I guess I think where we think that those effects are mediated by an anonymous market, that's where things may get easier in certain ways, right? And so that's, I think, what Guido was referring to in the context of that it doesn't matter exactly who the drivers are, it matters where they are at the moment and sort of what the density of drivers is near me, right? Or in some of Stefan's work, that there's this idea that it's all coming through this set of prices, right? And so then I think actually that puts a lot of really nice structure on the problem of dealing with spillovers. But there's other cases where we might not think that it has that structure, even if we observe some network of who people are interacting with. There's no reason necessarily to suppose that the structure of the interference is anonymous, right? That one of my friends may be treated, and that may have very different effects on me than if a different one of my friends is treated. And so, often we still impose those assumptions of kind of these kind of anonymous spillovers. But maybe in a lot of cases, it's a lot easier when it's all mediated through things like prices that are potentially low-dimensional prices. Right? Please.
To pile up on the problems a little bit. So if we go like 40 years ago and think about econ, right? So there were we had this things that started the credibility revolution. This was taking the con out of econometrics, or the Lalonde kind of study that showed that the observational methods could not replicate experimental methods. And so then that started this whole thing with the focus on the design, with the idea of doing RCTs, using instruments. And then now we go 40 years later and we look at the rise in causal research in economics. We see that causality goes up, but it mostly goes up in observational studies, where people use methods like diff and diff or other panel data methods, which fundamentally are regression-based methods, right? So they're not that different from what Lalonde was criticizing in the end of 80s. So the question is, how should we respond to that? Are we clear that kind of with this credibility revolution, we not ended up in the same place we were before? These methods, of course, are better validated, but still they rely on very strong assumptions. And so now we see that they constitute the majority of research that's labeled as causal, at least in economics.
Thank you. Let's move. Let's proceed in this direction so the microphone switch faster. Go ahead.
Okay. I'm going to briefly talk about heterogeneous treatment effects, which sort of related to what Andrea mentioned with external validity. And I'm going to refer to the targeting problem. So we have an institute at UCLA and at Berkeley that works with governments. And what they want to do, they want to effectively target programs, training programs, homelessness programs, criminal justice programs, and so on. And the best way to target would be if you had for each person what their individual treatment effect of that particular program was, right? Now, if you would teach applied economists about the fundamental problem of causal inference, it starts essentially with saying, well, it's very hard to get the individual counterfactual, we're going to replace it with a statistical counterfactual. And then we say, well, for a given experiment, we'll probably get a local average treatment effect. And that local average treatment effect, which is the average of those who complied to that experiment at the time and place, has been criticized in the sense that it's not general enough, right? But from the targeting point of view, it's too general, right? You can get the average treatment effect of a training program in California that may not mean very much for a training program in New York State, right? But what does it mean for the people in California? That may be very different. Right? And I could see two solutions, right? One is related to Guido's talk this morning. Well, a unit could be an individual. It doesn't have to be, Germany or California. It could be John Doe, right? And we could try to get a treatment effect for John in a panel setting, or people who look like John. And so we could get out of the problem by just increasingly using data. That's likely to be a limit, right? The alternative is theory, right? We could get an estimate of the distribution of treatment effects where we can, and then fit an economic model to then predict treatment effects to solve the targeting problem. Just bringing that up and passing it on.
Please go ahead.
This is a question for Professor Gordon that you mentioned is very interesting thing about. You said there's a revolution happening in political science, and you also mentioned maybe the field is a little bit weak. So I was wondering whether there is a causal question you can study here, right? Because obviously whenever those things happens, that's a moment to study whether this revolution actually is helping the political science or not helping. Should they get paid more? I'm being serious. Maybe there's a causal question can be studied here about the field develop itself with this kind of revolution happens.
Well, shall I answer? Do you want to answer or not answer?
I was thinking to do it in the end, but if you want to give a quick answer now or whatever.
So there might be various metrics that you would use to measure outcomes of success. But if, for instance, you just use the metric of are political scientists able to speak to a broad scientific audience, that is, do their articles get published in journals like Nature and Science, we can see that the potential outcomes framework and causally identified work is definitely improving the success of our discipline. That is part of why the people who don't do that work are so defensive.
Hey, hi there. I'm Matt Blackwell. I'm a political scientist, so I know well the weaknesses of our field. So I just wanted to speak a little bit and get maybe some thoughts to reiterate some things, which is that if you talk to political scientists, especially more traditional political scientists, a lot of what you get, and this was hinted at the presentation, is really an interest in the study of the causes of effects as opposed to the effects of causes. Right? Dean's slides are actually a good idea of this, which is like, you've seen this massive increase in effective polarization. What's going on there? Like, what caused that? And so then we go in and we try to flip it around and do an effects of causes analysis to try to solve that. Or another question is like something called the democratic peace theory, which is like, why on average do we not see democracies going to war with one another? And so there's been a massive literature in international relations that tries to answer that question using various degrees of success. So in political science, we also lack kind of an overarching structural modeling tradition, and so we don't have a lot of like formal models for that. So I'm just one thing that I'm curious about from the room and from folks on this panel about, is there a way that we can more systematically integrate studies of effects of causes into questions about causes of effects, right? And I think traditionally this was not seen as a distinction with a difference, because we thought of things in terms of constant effects terms. So that if you got something about effects of causes, you could also just kind of sum them up and get to the overall question. But I think as we've been more attuned to the ideas that there could be issues with heterogeneous treatment effects, and the thing that I identify with a very kind of interesting RDD municipalities in France might not generalize to every parliamentary versus or a first past the post versus a proportional representation kind of system. And so it seems like the connection between those two kinds of questions have gotten murkier as we've gotten more sophisticated on the effects of causes side. And I wonder, is that just going to be a fundamental murkiness that we're going to have to deal with, or are we going to be able to get some clarity in terms of how to really connect these two things and talk to those bigger questions through accumulated evidence?
So I guess I'm also a political scientist. Listening to Miriam, I remember the the paper by Jonathan Rodin, written back in 2008, where he was starting by saying like a fashion trend traveling from New York to the heartland. Causality made its move from economics to other social sciences. Gone are the days where you just needed some covariates in order to get into causality, and now you need a design-based method. But this is already like 20 years ago. I think we are way more into this now. The question I have is for the panel as a whole. There was almost by Andrea, by Miriam, a kind of an equalization of the causality framework with the potential outcomes framework. And in the same time, there was a discussion about the increasing need for structure. And I'm wondering if we are going to have to use more structure, whether there is also more room for the directed acyclic graphs framework of causality, given the need for structure.
Great, thanks. I'm going to stand because I'm so short. I'm Liz Stewart from Johns Hopkins. Thank you. This is great. And my question, I actually want to push the boundaries of what we mean by interdisciplinary, in that I think most of this room, except maybe tomorrow, one of the tomorrow speakers, is very quantitative. And one theme I heard was the value in working with substantive experts in terms of defining estimands. Also, I've thought about it in terms of assessing the validity of assumptions, of untestable assumptions. So just curious, partly this is me self-serving, I'm increasingly interested in the role of sort of formal mixed methods where we bring together formal conversations and sort of qualitative work with quantitative. So this is my plea. You don't have to respond now, but sort of would love just brainstorming around that as a group, around how can we sort of formalize some of these connections.
Yeah, thanks. Also on this interdisciplinarity point, I think it's very nice to have everyone in the same room from these different disciplines, but it almost feels to me that we have too much interdisciplinarity in the sense that the ability to use the same methods, take them off the shelf and apply them to very different contexts, actually can allow us to smuggle in implicit assumptions about how things work, which are not in fact tenable. And one of the ways in which the disciplines vary, and I think that these different disciplines on stage are very representative, is in the density of descriptive data. So even in the presentation this morning, we saw that the cross-country national level data had a lot more variance than the month-to-month wage data. So it seems like econ has quite a well-developed and kind of ontologically real, like a lot of people really care about wage data, whereas the kind of year-to-year variables political scientists can come up with to measure countries, almost no one really cares about, so they're not very well measured. And on the other extreme, the kind of data that Dean works with, the coming straight out of these platforms, is incredibly high density, minute-to-minute, second-to-second data. So it seems to me that one of the ways in which these disciplines vary the most, and the most importantly for how well we can do causal inference, is in the density of the descriptive data that we can use to actually do empirical meta-science.
Hi, thank you for the nice talk. Just a couple of words about the issue on spillover effects. I was thinking if we switch from, by considering instead of the individual, the firms, and then we might say a couple of words about which could be the role of those superstar firms in the economic framework. So which could be the intervention that regulators should do in this kind of context, because I think it's quite different from what you have been presenting before. Thank you.
Question?
Thanks. Thanks very much. I'm going to direct this question. I'm sorry, I'm Corey Ziegler from Brown University. I'll direct this question mostly to Dean, although I'm curious if anyone has thoughts. So in these problems where we have causal effects that are mediated by or dictated by some complicated, say, social network, and we don't know exactly how that works, I can think of sort of two branches of approaches to that. One would be come up with estimands or estimators that are really robust to the specification for how that might work, in the hope that they work under lots of different types of networks, let's say. And then another approach where we really devote a lot of efforts to understanding the network better so that we can build much more sort of bespoke specific knowledge in context. I'm curious if there are thoughts on sort of which of those directions should take priority.
Thank you. If we are done, you have about 7 minutes each to solve all these problems. Let me start with Miriam, and I will. You pick the one you want, then you.
I don't even know where to begin.
But we can continue also during coffee breaks and dinner and lunch.
So I do want to, okay, I want to respond to the concern that Matt Blackwell raised, which had to do with causes of effects and effects of causes. And I do want to ask why that difference is so fundamentally important. That is, and I mean that truly, like some of the questions I think political scientists most want to know have to do with causes of effects, and some of them have to do with effects of causes. And why aren't those the same?
Take the microphone.
They lead to different decisions.
Yeah, I thought there was a big theme like that was raised, like in terms of like frame your question based on the decision, but sometimes the decision is not necessarily an action, and so I think one aspect is I want to understand all the components, all the factors that are going to lead to that cause. You know, what is gonna, is an etiological question that then can partly inform, is more than addressing what action I'm going to take necessarily.
Okay, so let me just
wonder,
say,
again,
I imagine we can all agree that there is no way that we will ever know all of the causes of a particular effect. Like, that's just hopeless from the start, and so you don't really care about knowing all the causes. You care about, I think, knowing the size of the effect of what I will call theoretically pertinent causes. And so I don't think, we're not in a universe where we just want to like measure everything. So that if that's true, then I'm not sure I really understand the difference between these two things. But maybe.
So yeah, I want to make some comments on that. So I think that it is a really important set of questions, and one has not received nearly as much attention as it should have. But it is in my view, a very different question, looking at the causes of effects and the effects of causes. And one way to illustrate that is when we're looking at the effects of causes, we can typically conceptualize an experiment that would actually definitively settle that question. And for looking at the causes of effects, you can't really conceptualize that. And that reflects partly that some aspects of that question are not articulated very well in a way that really makes clear when we would have an answer to that question. And so very closely related is a question I've kind of seen a lot in the private sector where it's typically referred to as attribution. You kind of see some set of outcomes and now you want to attribute them to some well-defined, so even if that's a well-defined set of causes, but you want to attribute them to some set of causes. Who should get credit for this? And there's kind of different versions of that, but there's some fundamental difficulty in attributing credit to different components of an outcome that is similar to the trouble we have in identifying causes of effects. And I think there is actually a huge amount of work kind of on the attribution question and the challenge of doing this in settings where these causes are simultaneous, and so some of this relates to the Shapley value literature. But even in cases where it's not simultaneous, where it's sequential, it relates to a lot of the issues in the mediation literature where the trouble is that attributing indirect effects kind of one treatment on a second treatment are difficult. The effect on the outcome, the attribution of that indirect effect on the outcome to the different causes is kind of fundamentally not identified or not separable. and we need to bring in substantive information there to settle those questions. And I don't think there can be a statistical solution for that problem. So it raises a whole bunch of really important issues that have not been addressed in the causal literature very effectively, but they are important, and there's a huge number of settings where people very, very clearly ask these why questions, these attribution questions. But I have the floor. I do want to also comment on one other thing that was raised about differences between the disciplines. And while I don't really like kind of the discussion at the moment about, well, is political science this or that? I think there's been incredible work in political science on methodology, and it's the fact that it's integrated more with other social sciences has been very valuable. And there's clearly really novel ideas and interesting things coming out of all these disciplines. But I do agree that there are some differences in the type of questions these different disciplines ask, and it's sometimes the discussion about the merits of directed acyclical graphs and some of the approaches that have been used in economics, I think is related to that in say biological sciences, because I'm not an expert there, so what I say may not really bear much relation to reality. But my sense is that in the end the models there are sparser. If we look, say, at the causes for a particular medical condition, say the causes of cancer, there's sort of particular genes that matter and not other genes, and there's a lot of genes that don't really matter. In economics, you wouldn't really have that type of sparsity. If we look at, say, the causes of poverty, there's a zillion things that matter there, and we can't kind of narrow it down to one or two things that are driving most of the results. And I think that does inform sort of the type of methodologies people are using, where they're not building, where kind of, and partly as a result of the Lemur and Lalonde critiques in the 80s, we're no longer building these really complex models that rely on having a huge number of effects being absent. We try to build these smaller models where it's easier to ensure the credibility kind of these short chains of causal effects, rather than build these very complex models that just rely on a lot of assumptions that we really know are not credible. Andrew Gelman kind of once formulated it, I think, very effectively, as saying that in social sciences, all the correlations that are possibly there end up being there. And I think that is actually a fundamental difference between some of the say, biological sciences where there's a lot more sparsity in the world than there is in social sciences. But it doesn't mean we shouldn't be aware of what people are using there and try to kind of use the aspects of these models that are helpful there, and there are many of those, but we should be aware that there are differences in the questions and the world, the type of settings we study in these different disciplines.
Thank you. Dean, you want to?
Sure, yeah, and maybe I'll pick up there because I think this relates to one comment. So I think Kevin Munger was saying something about the kind of quality and density of data varying, and I think that actually is related to both some of these differences across areas, but also the questions of sparsity. Is that on a fine enough time scale, things can get sparser, right? So it can be that I'm potentially affected by what everyone else in the world is doing on a long enough time scale, but on a short time scale, there might only be in a particular window the set of people who are kind of right here and able to affect me in particular ways, right? And so some of that is kind of under the control of the sort of data collection that we do, and also that there's potential for different kinds of high frequency within subjects randomization that not only is changing the kind of just data collected, but is changing the design to create that kind of additionally sparse structure. So that's one thing I wanted to pick up on. And then one of the, I think there was a question about the relationship with qualitative work, and it made me think that sometimes this is a little matter of how you look at things, because I think about, like, I believe that, like, synthetic control was introduced as a method for case studies, right? So because it's really introduced as a method for studying an event that happens to a single unit, and maybe for kind of disciplining some of what you might try to do in making those comparisons, right? And there's actually a lot of that idea there that you might try to make comparisons of that unit to other similar units, and that you might rely more on some comparisons than others, right, is something that's implicit in a lot of qualitative research. So I guess in some ways maybe it's funny that I guess synthetic control has also, if you sort of think of that as like, oh, we're doing sort of a somewhat like quantitatively disciplined case study, maybe that's kind of a nice, more humble perspective to have on observational research of the kind that's done with synthetic control or diff and diff. So, and I think on that point, I know Dimitri also mentioned this, like, you know, has diff and diff been the biggest beneficiary of the credibility revolution? Well, basically means something that Lalonde had already showed was like not very credible. And I think that's an interesting point. And for me, one of the ideas that's beyond the specific potential outcomes framework or even non-parametric structural equation models or DAGs, one of the things that I try to use to discipline my thinking is thinking about randomized experiments and sources of random or haphazard variation. And it's often really hard to find that in diff and diff. It's actually really hard to find that in Guido's talk this morning. We're supposed to be provocative, right? So where was the design, really? There wasn't much of a role for design at all. So, you know, I think that's, when we do think we have some randomness there, that's really nice. So it would be interesting to think about, you know, I mean, I actually know, Guido, you have at least one paper about a kind of design-based version of diff and diff and kind of this panel data settings. But in some ways, one of the main things that paper does is show that the experiment that would justify what people are doing is completely implausible and bears no relationship to how policies are actually being rolled out, how units are deciding to adopt. And so I thought, you know, I mean, maybe that sometimes that's a useful warning, but I wonder if there's some way of improving that situation. And then I wanted to pick up, someone asked about different kind of perspectives on network structure, and I guess the perspective, at least I'm trying to explore, is really thinking about the decision making. So what would be the policy by which we're going to intervene on the network? What are the actions that we're advising individuals to take if they're trying to, say, improve their information environment around them or something like that? So that might be one way to drive it. And another one would be through having a generative model of network formation. But I think that's also such a process that involves so much strategizing, and we think that even if like kind of strategic network formation models from economics just produce really wacky networks all the time, there's something to the idea that we might want to have some kind of equilibrium concept. We might want to have some notion that people are strategizing when they're forming their networks, and that's not reflected in a lot of the random graph models that we have and that get typically used for networks. So I think there is a big hole there. I'm sure there's more we can discuss.
So Miriam, I had the impression that you wanted to say something while Guido was...
I did. So the only thing I wanted to say is if we cannot, one way to restate the conundrum that I think we in political science face, and that perhaps is faced more generally by social scientists, is that we can only identify effects of causes, but there are still questions that we need to ask, that we care about and the public cares about, that have to do with causes of effects. And that's kind of the dilemma, I would say, for our disciplines.
I may be provocative. So, yes, whether God exists is a very important question. There is no evidence. So do you really feel confident in giving to a politician an answer to this question, or to the question which we would really like to answer, but we cannot with a credible strategy, I do not. So I prefer to tell the politician, honestly, this is a question I cannot answer. Otherwise, I do what the macroeconomists do. I build a model. I think the model is a true data generating process, and I go to the politician and I say, this is the answer, but do we believe it? So then we have to accept that we are not omnipotent, and therefore some question cannot be answered.
Okay, so there has to be a middle ground where there has to be a way to forget about does God exist. We can't study that, and we can't even plausibly answer that.
There were people who were
But
studying.
we certainly can study and we can answer questions about whether people who go to church a lot because they think God exists have better health than people who don't. And so we can reformulate questions at levels that are more tractable. And I would encourage that.
I think you know reformulated as an effect of...
Wait a second. Can you get the microphone, please?
Yeah?
Can you get the microphone and repeat? The microphone?
Yeah, I just say... By sharpening the question, you actually made it to a question about the effect of causes and not the causes of effect. And I think that illustrates the point. So I'm a medical doctor by training, and what we want to do is interventions. And when you push them into the wall, they will reformulate in this way as well. Although they, in a conversation in daily life, they would say, I would like to know the causes of breast cancer. But
Guido, you want to?
Yeah, I agree with the fact that if we ask people what decisions they're actually thinking about, that helps make it into the questions about the effects of causes. And implicitly, when they're asking for causes of effects, they do have some decisions in mind, but they may be different decisions, and the answers that are going to come out of that, the answers are going to depend on that.
And actually, I think the decisions there are often like further investigation. So I remember I did my studies at Stanford, and I think there was a time when absolutely everyone in the statistics department there was doing something with GWAS. And this is probably true in a lot of statistics field at the time, right? So there's all this high-dimensional kind of data, and you're trying to figure out which markers are going to be predicting pancreatic cancer, right? And so you're looking across all these different potential causes, right? And maybe there's sparsity, and maybe that helps you, right? But I think how Trevor Hastie put it was that the decision you're making is whether to allocate a life of a PhD, a year of a, not the whole life, just a year of a PhD student's life to this gene, right? They're going to go do something with this gene, and if you were wrong, right, then you've maybe wasted a year of their life, right? But if you're right, and so the decision is actually this, like, to then do something that we think would be a more robust way of learning about the effect of that particular cause. But you're kind of initially screening it through what, maybe something like a big linear model like a lasso or something like this. So,
question there, and then the final remarks.
Yes, and I know we're running out of time, but I wanted to just thinking about two examples of thinking about the causes of effect that had very negative consequences in society. So one example, and of a statistical analysis formulated in terms of causes of effect, was a paper in Science. Tomasetti is the first author of many years ago, which has tried from a mathematical statistical viewpoint to try to figure out the causes of cancer progression from a biological viewpoint. And if you're trying to estimate from a mathematical viewpoint what is the most important causes of cancer mutation, what's happening is a bigger part is random. And so I don't know if you heard, and if you Google, said cancer is a bad luck. That was a devastating news because it basically kills the entire research of cancer prevention. Because if you formulate the problem about what is the most important cause of cancer prevention from a biological viewpoint, it's random. right? So if you go on Google, cancer is bad luck, it brought back 50 years of research in cancer prevention because it got monopolized as, well, if you get cancer, it's bad luck. The other example where it's also very dangerous of the formulation of the different causes and effect is climate change. And tomorrow, Marshall Burke, here you are, Marshall. Marshall will give you an example of the other very important question, which Guido mentioned, is attribution. And so the question is, if you're thinking, what is the cause of climate change? Is man-made or it's not man-made, right? And that's another situation where it can be really hard to disentangle the different causes of climate and how a quantification of that causes, again, can be manipulated by the fact that, you know, we are not the responsible. So I think this was a really interesting conversation, and thinking about formulating in that way actually could have a really negative consequences on the analysis.
So any final comment on this point?
I think this is all very interesting, and it shows there's just a huge amount of work still to be done. I think these questions about attribution and why questions of causes of effects are very interesting. I think we'll see a lot more work on that.
So thank you very much to everybody. I think we can conclude that a causal effect of putting together smart people in a room is that you get a very interesting conversation. Thanks to everybody for participating to this roundtable.
We have lunch here now, and we reconvene at 2 o'clock. Lunch is here again. You can take your plate and go outside.